All right, good morning, everyone. We're starting, sorry for starting a few minutes late. We have technical difficulties as expected, of course. But it's great that you're here for the start of the consequences part of this workshop. I'm going to give you a short introduction on what we're going to do today. But first, I want to thank the organization team. So today, Olivier, Yuta, and me will be there, but I also want to thank Thorsten and Flavian for helping organization of this workshop. I also want to give a shout out to the Reveal workshop, some of whom helped with the reviewing of the papers that you're going to see today. So why did we want to organize the consequences workshop? The idea for us is that we wanted a place where we talk about recommender systems as decision-making processes. And when you look at recommendation as decision-making, you get an interventionist view, where recommendations are interventions with significant consequences. And with that view comes natural questions of counterfactuals, or the what-if questions, causality, sequential decision-making, and all that. And those are the topics that we're going to talk about today. To give you a brief overview of what we have planned, we had a single call for papers together with Reveal. So all the papers were submitted to both Consequences and Reveal. We then divided the papers per topic, and we ended up with 10 papers in total. They all have a poster presentation in the hallway. There's going to be 7 paper talks today, 2 keynotes, and 1 tutorial. I made a word cloud out of the titles of the papers, and you can sort of see what the main topics are going to be today. A lot of evaluation, a lot of policy, a lot of causal, some neural, and of course, some recommendation. To give you an idea where the authors are coming from, I put all of the authors into a sheet per affiliation, and I didn't normalize these per paper. So Amazon, you see here, we have the most Amazon authors for sure, but it could be, it's not that they have 8 times as many papers. They also have a lot of authors on their papers. But it does give you some idea of what kind of talks we'll be seeing, a nice mix of industry and academia. We have 2 keynotes. So the first keynote is going to be from Lihong Li, Senior Principal Scientist at Amazon, who's going to talk about decision-making recommendation from a reinforcement learning perspective. The other keynote is going to be by Guido Imbens. Yes, yeah. Professor of econometrics at Stanford. You may have heard of him because he's a co-winner of the Nobel Prize in economics in last year. He's going to talk about randomization designs, how to do causal studies in general. Then this is our program. We have a morning program and an afternoon program. We're going to start with the tutorial, and then we'll have a poster session. Then we'll have the first keynote and a paper session. Then you have 1 hour to have lunch. And when you come back, it's going to be the second keynote, another paper session, and a poster session, and then finally the last paper session. All right, then that leaves me to introduce our first speaker, which is Yuta Saito. He's a first-year PhD student at Cornell University, advised by Professor Thorsten Joachims. You may have know him from last year's RecSys tutorial on counterfactual inference. He's going to give a slightly different but shorter tutorial for you now. You may also know him as one of the authors of the Best Paper Runner-Up Award at Wisdom 2022. He's also been admitted into, or is listed in Forbes Japan 30 under 30 a couple months ago. So it's a pretty good start for a first-year PhD student, of course. Please welcome Yuta Saito.
And thanks for the introduction, but I became a second-year PhD just last month. So let's get started with the workshop tutorial, approaches to policy variation in large action spaces. Again, I'm Yuta Saito. I'm a second-year PhD student in the Department of Computer Science at Cornell University. So why workshop tutorial? I think this kind of workshop tutorial has never been implemented in any other workshop, I guess. But there's some motivation there, right? You want to make sure that everyone shares the basic formulation, basic knowledge about counterfactual estimation or policy evaluation more in detail. At the beginning of the workshop should be useful for in-depth discussion throughout the day, I guess. We want to also discuss very recent, exciting topics in the relevant area and also corresponding future directions. We plan to do this kind of workshop tutorial every year. We plan to pick one specific tutorial topic every year, and this year's topic is going to be large-scale policy evaluation. Should be very relevant to recommender systems and search engine, how to perform or how to implement offline evaluation of policy evaluation of some new counterfactual policies using only the log data. That's the topic for this year. We will also promote some research collaboration, right, in-depth research collaborations in the relevant, very important directions throughout the day. So I want to mention that, right, the tutorial slides are now available on the workshop website. So of course you can see the screen, but it's also possible that you can just see the tutorial slides in detail. So here's the outline. The talk is roughly about 75 minutes, I guess. And we're gonna have 10 or 15 minutes Q&A at the very end of the talk. As Harrie mentioned, right? You can post any questions throughout the tutorial through this Q&A system, stuff like that. So there are 3 sections in this tutorial. So the first section is basically about just a quick intro to standard policy evaluation. I basically assume that many of you are familiar with the basic formulation of causal inference and counterfactual estimation stuff. But basically, I want to make sure we are on the same page about notation, which I'm gonna use throughout the day. It's just a very brief intro to the statistical estimation problem, and also I'm gonna go through very briefly some benchmark estimators in this area. And then I'm going to talk about 2 main topics. The first one is how should we perform policy evaluation of ranking policies rather than very simple single action policies, right? So of course, we're talking about we're all interested in recommender systems, so we should be actually interested in offline evaluation or off-policy evaluation of ranking policies rather than a single action, very simple, bounded policies. And then finally, I'm going to also talk about a even more recent topic, which is how to deal with a more general type of large action spaces rather than assuming some very ranking specific assumption. Maybe we can use some action features or some auxiliary knowledge about the actions for the purpose of off-policy evaluation. Okay, so that's basically the outline. So then let me jump into the quick intro to standard policy evaluation, which is going to be maybe just a 10 or 15 minutes, just a very brief introduction. So speaking of policy evaluation, it's basically all about automated decision-making algorithm, like bounded algorithm or reinforcement learning algorithm. So the canonical example is item recommendation. Of course, that's basically the reason why I think it's very exciting to talk about of policy evaluation in this RecSys conference. So we always want to optimize some kind of decision-making policy, right? In this case, what kind of recommendation we should apply to common users. So our goal is just to maximize some notion reward, maybe create or convergence, basically whatever you want, and not just to make any accurate supervised predictions. So there are many applications in the industry. So right, there are growing number of papers talking about how to improve the decision-making quality of contextual bounded algorithm, or maybe structures bounded or offline reinforcement learning very recently. But of course, the topic of this talk, the topic of today, is more like a evaluation side or kind of factual estimation or offline evaluation or off-policy evaluation. So the question here is how can or how should we evaluate the performance of some new decision-making policies, but using only the historical log data collected by logging policy or past policy, right? So of course, if we could implement some A/B testing stuff, we can always have some accurate estimation or on-policy estimation of the decision-making policies. That's great. But sometimes we don't want to implement A/B testing, might be risky or might be very costly, right? So, and also maybe it's impossible sometimes to apply A/B testing to many different candidate policies, possibly having different hyperparameters. So it's always, right, it's very often very useful to have this kind of offline evaluation option using only the historical log data without having any A/B testing procedure. So there are many papers. Again, it's a very practically relevant problem, I think. So there are many growing number of papers talking about how to perform accurate policy evaluation, maybe developing some accurate estimators. But the thing is, it's still very difficult to deal with the large action spaces or large scale problems. What I mean by that is all these, recommendation or recommender system application are basically very large scale, right? What I mean by large scale is they're basically, right, there are thousands of millions or even more number of action, I guess. It's actually very crucial to be able to deal with large action spaces when performing policy evaluation in the industry scale, exactly the recommender system application, especially. But the thing is, again, right, it's actually very difficult. Still, it's very difficult to deal with large action spaces, even given some recent advances in off-policy evaluation. Of course, I'm going to talk about more in detail this kind of issue in a few moments. But this is exactly the topic of today. How should we perform policy evaluation in large discrete action spaces or medium number of actions? But before going into the very detail of this large scale policy evaluation stuff, let me just briefly go through the standard policy evaluation and some basic formulation. So I'm going to basically focus on contextual bounding setup. which is of course much simpler than reinforcement learning. I mean, the maybe topic of yesterday. But I think it's still very useful to discuss this basic contextual minded setup. So here's a common data in the process, or how a log data is generated by a logging policy. It's basically just a contextual bounding process, right? It's very simple. We first observe some context X from unknown environment PX as a user features or user information. And then a logging policy or path policy or running policy stochastically picks an action A, maybe just a movie recommendation or some product recommendation. I want to mention that for now, right, this is just a single action policy rather than ranking action policy, just a standard policy variation setup. And we finally observe some reward, given context X and an action A, clicks or conversion or basically whatever you want as a reward. And the logging policy interacts with the environment again and again and again following this process and produces some log data set collected by the collection of context action and the reward, just a contextual bounded data set. So we see this data as a very useful source for performing off-policy variation, whose goal is to accurately estimate the value or the performance of some evaluation policy or some new policy, right? So there is a common definition of the performance or the value of evaluation policy, which is very simple, right? Just the expected reward under the deployment of the new policy or evaluation policy, right? So of course, we don't want to implement this evaluation policy, actually implement this evaluation policy in the online environment. So our goal here is to estimate this, estimate our value of evaluation policy using only the log data. So what we want to do as a researcher is to develop an accurate estimator. So V hat is an estimator that hopefully accurately statistically estimate the expected performance of the evaluation policy. But what's important here is we can use only this historical log data, which is given by the logging policy. Of course, the logging policy is different from the evaluation policy. So when developing an estimator, we need to address somehow it's kind of a distribution shift between evaluation policy and a logging policy, one of the key challenges in counterfactual estimation, of course. So accuracy of an estimator is often quantified by MSE, both in theoretically and empirically. So MSE is just an expected square distance between the estimate and the policy variation result. Can be, of course, decomposed into the squared bias and the variance, right? So roughly speaking, the bias and the variance are equally important to achieve a small MSE, right? So when we want to develop, or when we try to develop or design a new estimator, we need to basically care about both the bias and the variance. So this is actually one of the key points later in the talk, right? So again, bias and variance are equally important in terms of MSE. So that's basically the basic statistical formulation of a policy variation, right? We want to estimate the expected performance of the new policy by using only the log data, and the accuracy is basically quantified by MSE, right? We want to develop an accurate estimator in terms of MSE. So it's a basic setup. And let me also go through some of the benchmark for basic estimators in this area. So maybe the first benchmark estimator I should definitely introduce is a direct method, or maybe the heuristic reward estimation method. So this direct method very simply, first of all, estimate the expected reward function given context X and action A, maybe using some off-the-shelf supervised machine learning method. Maybe you can use random forest or some other maybe deep neural network based on your validation results. So we're going to have this R hat, which is an estimator for the expected reward function. So maybe we can see this reward estimator as a reward simulator, right? So at least we should be able to run this evaluation policy on this reward simulator. So this is basically how this direct method estimate the value of evaluation policy. We first of all run this reward model, and then we can learn the evaluation policy on this reward simulator, for example. So there's some pros and cons, of course. The one good thing is this direct method is basically very low variance, very stable, right? So this means that even given some random draws of the log data, we basically have a very similar estimation result of P good. But the thing is, right, this direct method is often highly biased when the reward model is misspecified or inaccurate, right? And it's often the case that in your practice, it's very difficult to estimate this reward, expected reward function, right? Basically the reward is basically very noisy. So the direct method is often introduced as a very high biased estimator, right? So high bias and a low bias estimator, which is a direct method. So the other estimator, another estimator I need to introduce, of course, is inverse propensity score. I think there are some talks about this IPS estimator yesterday at the review workshop. So this is just an importance weighting or importance sampling to unbiasedly estimate the policy value, right? So it's a free model-free approach. There's no reward estimation stuff here. So the definition is extremely simple, right? Just like empirical weighted average of the observed reward, and the weight is vanilla importance weight. So the reason why I call it this vanilla importance weight is there are several other versions of importance weight later in the talk. So I sometimes call this a vanilla importance weight, just a ratio of the variation policy and the logging policy. So the point of having this importance weighting term is, by having this importance weighting, we can guarantees unbiasedness and consistency under some identification assumption. If you are interested in the, the identification assumption, maybe some like unobserved confounder stuff, maybe you want to refer to some causal inference text. But anyway, we can basically very easily ensure unbiasedness and consistency. But could be very unstable high variance, right? For example, like small sample size or large action spaces, which is definitely our main topic. And also the noisy rewards is basically a very high variance setup. So IPS might be very unstable estimation, even though it's theoretically unbiased. So just to be a little bit more formal, right? IPS is unbiased and consistent. So the expectation of this estimator is equal to the estimate, and also does converge to the true positive value within finite sample data. So there are some assumptions, as I said. One assumption I want to particularly mention here is the common support assumption, which is basically the verifiable assumption, but requires that the login policy to cover every action that could have taken under the evaluation policy. Otherwise, we don't have any information about some actions in the log data, so the IPS might have some bias. The reason why I mentioned this common support assumption here is actually there's another version of the common support assumption later in the talk that enables a comparison of different versions of common support assumption. But anyway, under this kind of identification assumptions, IPS is unbiased and consistent with a remarkably simple implementation, making this estimator very popular in practice and also in research as well. So here is the basically the common kind of comparison of direct method and IPS to get some intuition on the very different type of bias trade-off of these two estimators. So what I'm doing here is very simple, just a synthetic, using synthetic data, we can actually very easily compare the accuracy, I mean the MSE of these estimators with a different sample size. So the y-axis is MSE, the was more accurate. And in the x-axis, I increase the sample size from 100 to kind of 6,000. Right, the blue line is direct method, and the red line is IPS. And in the small sample size, we see that right, the IPS seems to be very unstable. Right, its MSE is basically equal to its variance. Right, it's theoretically unbiased. But the direct method seems to be relatively stable or low variance. But if we increase sample size, right, IPS is getting more accurate with increasing sample size, reducing its variance, and also it's basically unbiased. But we see the direct method, right, is actually remains highly biased even though we increase the sample size. So we basically see exactly the opposite kind of behaviors due to the very different statistical properties, I mean, the variance trade-off. So this is basically the very high level understanding of the different properties or different behaviors of direct method and IPS. So of course, there's one additional aspect I should definitely introduce in this quick introduction. Maybe most of you are very familiar with this doubly robust estimator, I guess. This is also very popular and useful in the policy validation of reinforcement learning policies. So the high level idea is very simple, right? As I said, there are two basic estimators, direct method and IPS, and they have very different statistical properties when I mean variance trade-off. So maybe the very simple idea would be why not, right? Why not simply combining or unifying these two basic estimators, I mean direct method and IPS, to do much better than both. And this is exactly what this doubly robust is doing. Of course, there are some other more complicated explanation behind this doubly robust. There are some more theoretical ones. But this is maybe just a very intuitive explanation, why not combining these two estimators? That's basically it. So here is the definition of this doubly robust estimator. There are basically two terms. So the first term is just direct method, one of the basic estimators, right? So let's have this direct method as a baseline, which is very stable, but could be highly biased. So let's also have a bias correction term via importance weighting. But the trick here is importance weighting is applied only to the residual of the reward model, resulting in some variance reduction compared to the IPS, the original IPS is better. So this doubly robust is unbiased and consistent, even though we use possibly highly biased direct method as a baseline. And what's also nice about this doubly robust is, of course, very often we can have a lower variance than IPS. So definitely, dominating the IPS estimator in terms of variance trade-off. So there's some recent estimators, but many recent estimators are actually heavily rely on this doubly robust definition. Okay. So let me also additionally compare this doubly robust estimator in the synthetic experiment used earlier. So I just additionally, including this doubly robust in the purple line. So the y-axis is still MSE, and in the x-axis, I just increase sample size from 100 to 6,000. And we see clearly that the doubly robust does reduce the variance of IPS in almost all cases. It's also true that in extreme small sample size, doubly robust might still have some high variance. The reason is it's still using the vanilla importance weight. That's exactly the source of high variance. But basically, the doubly robust achieves the lower variance compared to IPS almost always. if we increase sample size even more, and then we can clearly see the consistency and consistency of IPS and WBUST. But the thing is, WBUST does converge much faster than IPS due to its efficiency, or roughly speaking, the lower bias. So that's basically the high level understanding of the benchmark estimators, direct method, IPS, and the combination. I mean the WBUST. Okay. So of course, there are many more recent advances in this standard policy variation. What I mean by standard policy variation is a discrete single action, and also the number of actions is not so large, right? Maybe 10 or 20 actions. So there's a very popular WBUST, and on top of WBUST, there are many advanced estimators recently, maybe switch WBUST or shrinkage WBUST. There's also like a more robust WBUST and a smoothing WBUST, which was proposed just last year's new LIPS conference, a very recent ones. But what they're doing is actually very simple. They just basically modifying the importance weighting part on top of WBUST, aiming for further variance action, right? But this is actually just a standard policy variation, so this is not the main topic of this talk. So if you're interested in this recent line of work in standard policy variation or maybe policy learning side, maybe you want to refer to our last year's RecSys main conference tutorial, which is about 3 hours, a much longer one, but on counterfactual learning and counterfactual evaluation. We talked about this basically standard policy variation and policy learning and some implementation stuff. And the full recording of the last year's tutorial is now available on RecSys YouTube channel. So if you're interested, please just refer to this full recording of the last year's tutorial for the standard policy variation. But anyway, this is a quick intro to standard of policy evaluation, just reviewing the basic statistical estimation problem, the policy evaluation problem, and also go through the benchmark estimators of direct method IPS and WBUST. Then let me talk about the main topics. The first one is how should we perform a policy evaluation of ranking policies? Definitely, very relevant to the RecSys community. So again, in the previous section, I talked a bit about the standard policy evaluation, but considers only like single action policies. Definitely overly simplifies it up compared to what we see in practice. So I think I don't need to mention in this crowd, but in practice, the action space is often ranking or combinatorial stuff. So we're actually interested in how to perform offline evaluation or off-policy evaluation of this type of ranking policies rather than just a single action policy. So let's talk about the policy evaluation in the case of ranking policies from now. So to discuss the ranking policy stuff, we need to actually modify the formulation just a little bit to capture the ranking setting, but this is just a very simple stuff. So let me just introduce this position index K to just differentiate each different position in a ranking action, right? So A subscript K is just an action, maybe a product from a movie, chosen by a ranking policy at a particular position K. And similarly, a reward, RK is a reward, maybe clicks or conversion, depending on how you define your reward, observed at a particular position K. Right? So we may have several different action observations and the reward observation, each corresponding to different position K. That's basically it. It's arbitrarily just a one single ranking action. So we are still interested in the estimation of the value or the performance of some evaluation policy or new but ranking policy, right? So there is the value of evaluation policy in the ranking case. This is basically the same, just the expected reward under the new policy, new ranking policy. Maybe one thing I need to mention here is we commonly use this kind of additive ranking matrix when defining the value of a ranking policy. So alpha is just a customizable weight, maybe the importance of each position K, maybe it's specific to every different application. But by just customizing this alpha weight, we can actually represent basically any type of additive, the famous ranking matrix like DCZ or precision or number of clicks. So what we want to do in the policy evaluation ranking policies is to estimate, for example, the expected DCZ under the new ranking policy, but of course using only the historical log data given by a different ranking policy, the login ranking policy. So at high level, it's basically the same problem. But we be interested in the estimation of this kind of additive ranking matrix in the ranking case. Okay, so how should we do this? Actually, the important starting point when thinking about this kind of policy evaluation of ranking policies is actually, even if we want to evaluate this kind of ranking policies, we should still be able to apply IPS and many other related estimators to at least get an unbiased and consistent estimate, right? So here is the ranking version of IPS, but to me, this is exactly the same estimator compared to the original IPS in the previous section. Of course, there's some difference in notation. For example, I'm now defining the importance weight in the ranking level rather than single action level. I'm also using this additive ranking matrix, but this is just the scalar value, right? It's basically the same. So, right, at the end of the day, just a ranking action is just a discrete action. So we should be able to very easily apply this kind of IPS estimation to get an unbiased and consistent estimate, even in the ranking cases. So this also implies that any estimator in the standard of policy evaluation, maybe including W-bus and some other advances in on top of W-bus, can also be easily applied to the ranking policy evaluation, like I'm doing here. Right, so it seems pretty good, right? We can utilize any recent advance in standard policy evaluation very easily in also in the ranking policy evaluation. It seems pretty good. But unfortunately, the thing is, of course, right, that kind of naive application of standard policy evaluation often or almost always doesn't work at all in the ranking cases. So there seems to be the unique issue in the case of ranking policies. And of course, the thing is, right, the ranking action spaces or the number of action or the number of ranking grows exponentially large in the case of ranking policies. So it's actually causing the extremely notoriously large variance issue in almost all policy evaluation estimator in the standard policy evaluation, right? So we should actually deal with this kind of exponentially large ranking action spaces when thinking of this kind of the policy evaluation of ranking policies. So maybe just to get some intuition, suppose there are 100 unique actions and a 3 position, definitely a very small scale problem compared to the Leo recommender system, of course. But the thing is, of course, we now define the importance very differently for each unique action. We need to, of course, consider every different unique computation of the ranking. And in this case, the number of actions or number of unique rankings is going to be nearly 1 million, even though there are only 100 unique actions. So this is exactly the problem what I'm talking about, right? So the number of rankings or number of unique computations grows exponentially large, grows exponentially fast, so causing extremely or notoriously large variance in almost all standard for exploration estimator. So of course, right, we can naively apply or very easily apply any standard for exploration estimator to the ranking setting. That's true, but that kind of naive application doesn't work at all to do this kind of exponentially large ranking action spaces. So maybe I can also provide some, empirical understanding of the variance issue or the inaccuracy of IPS with growing number of actions. So here I'm basically showing a very similar figure I used earlier, but here I'm fixing the sample size of the number of data at 3,000. Instead, I increase the number of actions from 10 to kind of 2,000. So 10 is like typical policy evaluation experiments done in many research papers. This is definitely small scale, right? Unfortunately, compared to the real practice. 2,000, I think, is still a medium scale, not a large scale. But the thing is, 2,000 is enough to see the inaccurate or unstable issue of IPS. So I think to everyone, it's already obvious, right? The red line is IPS, and this IPS estimator is getting significantly worse with growing number of actions, given the fact that the y-axis MSC is on a log scale. And also this IPS estimator is even worse than a bias baseline and capacity in the presence of many actions. And the reason why we see this kind of very inaccurate or impractical behavior of IPS is basically due to the importance weighting term. Right, so importance weighting is also growing with a growing number of actions, definitely causing instability or high variance issue of IPS. And the point of having this kind of a synthetic illustration is, right, so this is happening, this very undesirable behavior is happening, even though there are only 2,000 number of action, right? Going back to the previous slide, even though there are only 100 unique action, we need to address, or we need to work with, nearly 1 million number of unique rankings. So definitely the critical variance issue there when thinking about ranking policies. So again, the critical variance issue there due to the ranking or combinatorial action spaces, exponentially large ranking action spaces, which is definitely very practical challenges, right? Always when we think about the policy evaluation of ranking policies, we should definitely be able to deal with this kind of ranking action spaces. So there are some recent papers talking about how to potentially deal with the ranking action spaces. Of course, there are lots of future work to be done in this direction. But today, let me introduce one interesting or one promising approach to potentially to deal with ranking action spaces. So the idea is we might be able to introduce some assumptions on user behavior in the ranking, or how user behavior in a ranking, or how user behavior in a platform, to make at least the ranking action space is much more tractable. Or maybe we can see this approach as a hybrid or combination of the click modeling approach or behavior modeling approach in information retrieval and of policy evaluation. And by combining or by utilizing some knowledge from user behavior modeling, we can actually design or define some ranking specific estimator that can substantially reduce the variance by doing nothing by, compared to the original IPS. So here, let me introduce just a couple of estimators, couple of concrete example in this fraction. Maybe just to get some high-level intuition or high-level understanding of this very flexible, very general framework. And the goal is we want to be actually able to utilize this high-level idea, and we want to be able to design our own estimator by ourselves by maybe combining appropriate behavior models and advanced policy evaluation specific to application. So let me just introduce a couple of estimators to get a high level understanding of this very general idea. So the first estimator I should definitely introduce in the instruction is an independent IPS or VAE-IPS estimator, which is based on a very simple or maybe overly simplified assumption of an independent behavior assumption, which very simply assume that users in a platform interact with the items in a ranking totally independently, right? Or in other words, when we look at the third reward in a ranking, for example, so let's consider only the effect from the corresponding action or corresponding position, right? So let's ignore every possibly complex interaction from any other position in the ranking. So that's basically the assumption. But maybe we can say that it's sufficient to condition on the case action in a ranking to specify or characterize the reward function or the reward expression, right? We don't need to look at the entire ranking list. It's sufficient to condition on the case action because we now assume that the user behavior is totally independent. Okay, so maybe I need to mention that this independent assumption is basically overly simplified compared to real user behavior. But the thing is, our motivation here is to design a accurate, ranking specific estimators or ranking policy variation estimators in terms of MSE, which is the bias plus the variance. So our motivation is not to precisely describe user behavior here, but rather we want to design an accurate estimator in terms of MSE. So the point here is sometimes it's totally okay to have a intentionally or overly simplified assumption if we can reduce the variance substantially, or if we can design a new estimator which is better in terms of MSE. So that's basically the idea here, which is the motivation is very different from the behavior modeling or information retrieval. What we want to do is to design an accurate estimator. But anyway, this is one assumption, one possible example assumption, and based on this independent assumption, we can define a corresponding ranking specific estimator, which is called an independent IPS, which is defined like this. Of course, looking very similar to the original IPS estimator, the foundation is basically the same. But the important difference here is I'm now defining a position level importance weight rather than the ranking level importance weight, and the importance weight is also now inside the summation over K. Okay. So what I'm doing here is just defining the importance weight independently for each position K, resulting in substantial variance action compared to defining the ranking level importance weight or differentiating every different unique ranking action spaces. So just to go through the statistical properties of this independent IPS. So this is unbiased and consistent under the independent user behavior assumption, which is of course unlikely to be true, unlikely to be true in the platform. But that might be okay because we can reduce the variance greatly, right? We can reduce the variance substantially compared to the no assumption IPS. But of course, we could have a large bias depending on, I would say, like a divergence between the assumption and the new user behavior. So what I'm doing here is kind of introducing a very interesting type of a bias variance trade-off structure in policy evaluation, which is now controlled by what kind of user behavior assumption we impose when designing a new estimator, right? So again, always this important starting point is this kind of a no assumption IPS or the general, the original IPS, whatever you call it. This is generally unbiased without having any ranking specific assumption like behavior assumption, but could be notoriously or extremely high variance. So this is basically useless in ranking action space, I would say. So one thing we can do is to assume a very simplified assumption of an independent assumption resulting in independent IPS. The good thing is that we can reduce the variance substantially, basically always, but we may have some bias depending on the complexity of the real user behavior, right? So the point here is, of course, the optimal estimator or the best estimator, the appropriate estimator can be different given different situation or given different problem instances. So what's important, what's desirable here is to have a wide range of bias variance trade-off we can choose from. So let me also introduce one more recent estimator that can provide additional trade-off we can choose, which is also like in the middle between the no assumption IPS and the independent IPS. So the next estimator is the more recent estimator is the reward interaction IPS just proposed at a Kennedy conference a couple of years ago. So this estimator is also based on another assumption or another user behavior assumption, which is a cascade assumption, which I think is a very famous and very popular in this crowd. So which very reasonably assume that user in a platform interact with the items in a ranking in a sequential way, but we now assume that the users are coming from the top to the bottom position, right? User examines the items in a ranking one by one from the top to the bottom. Well, maybe we can say that when we look at the third reward, we can consider only the top K action simply because the users are coming from the top. Well, it's sufficient to condition on the top K actions when specifying or characterizing the expected reward function or the reward expression. Okay, so it seems to be much more at least reasonable compared to the independent assumption. And based on this cascade cascade assumption, we can also design another corresponding estimator, which is a reward interaction IPS. So looking a little bit, maybe a little bit complicated compared to the independent IPS. What I'm doing here is pretty simple, right? Just defining the kind of the top K importance weight rather than ranking level importance weight. So maybe the intuition is when we look at the case position, or when we want to evaluate the value or the behavior of the policy at the case position, again, we need to only consider the top K actions because users are now assumed to be coming from the top. So we should define this kind of a top K importance weight to make it unbiased. So this estimator is unbiased and consistent under the cascade assumption, which is more likely to be true compared to the independent assumption, of course. And we can still, right, greatly reduce the variance of the no assumption IPS by utilizing this kind of assumption, but may have a larger variance than independent IPS and a larger bias compared to the original IPS estimator. So again, maybe the best estimator can be very different given a different situation. What I'm doing here is to introduce some concrete, 3 examples in this line of combination of behavior modeling and the policy evaluation estimator, right? So there's a no assumption IPS and a cascade IPS or reward interaction IPS, and finally the independent IPS. So one important message was one important understanding of this bias variance trade-off is, again, the appropriate estimator can be very different. So you don't need to choose one estimator out of 3, but rather you may want to leverage this kind of a high-level idea of the behavior modeling and the policy evaluation to develop your maybe own estimator when you rank a specific estimator by yourself by combining an appropriate behavior assumption, which might be specific to your application, and maybe more advanced estimator. So, right, again, you don't need to necessarily pick one estimator out of these 3 estimators, but rather you should be able to design your own estimator specific or appropriate to your application. So one such example is actually the more recent work in this line of work, which is a cascade of W-robust. So conceptually very simple, right? So as done in the standard policy evaluation in the previous section, we should be able to actually extend, for example, the reward interaction IPS to what we call like a cascade of W-robust. Right? Well, why not using this kind of a W-robust estimator in the cascade assumption? So the idea seems to be very simple, but actually turned out to be not so simple or not so trivial. So the reason is it should be not so clear what would be the correct definition or appropriate definition of W-robust in the case of a cascade assumption, because cascade assumption is kind of a sequential assumption. So it should be not so easy to define or correctly define the W-robust estimator under the cascade assumption. But what's interesting about this work is we can actually utilize a structural similarity between the cascade model, right? Examine the items in the ranking 1 by 1 from the top to the bottom position, and also the reinforcement learning formulation, which is a Markov making process, to correctly define the cascade W-robust. So here is the definition of the resulting cascade W-robust estimator. If you are familiar with the reinforcement learning policy evaluation, maybe you might realize that this estimator looks actually very similar to the W-robust definition in the case of reinforcement learning policies. But what's really interesting about this definition is we're still working on a contextual banded set, or we're still working on the contextual banded ranking policy stuff. But the resulting estimator looks very similar to the reinforcement learning. And the reason is we actually utilize the similarity of the cascade model and the reinforcement learning formulation for each user within each user behavior in the ranking. Right? So at the high level, we're still working on a contextual banded, but the resulting estimator is very similar to reinforcement learning by utilizing kind of the reinforcement learning-ish user behavior, which is a cascade assumption. But anyway, there's some variance analysis of this cascade W-robust. In particular, the variance reduction analysis looks very similar to the reinforcement learning policy evaluation, but intuitively, this cascade W-robust reduces the variance of reward interaction IPS, and also, of course, the no assumption IPS as well, while being unbiased and consistent under the the more reasonable cascade assumption. Okay. So there are some empirical results. Just a few words about synthetic empirical results. So there are some synthetic results. So we can actually control the true user behavior that generates the data. So the right-hand side is the very complex behavior where we cannot, assume any specific user behavior. And this one is a cascade behavior and also the independent, very simple behavior. So the one thing that maybe I need to mention here is definitely the best estimator, the appropriate estimator can be very different depending on different data generative processes or the data, the true user behaviors. So it's actually very desirable to have many options about the bias variance trade-off you can choose from. And also it's very important for you to define or design your own estimator by utilizing or leveraging the high-level idea of this combination of behavior modeling and policy evaluation estimator rather than just picking one estimator out of the several previous estimators. And another very interesting maybe observation about this empirical result is, so when we look at this first figure where the behavior assumptions is not true, Even though, right, the cascade assumption or some other assumptions are not true, we can see in many cases that the cascade W reversed or the reward interaction IPS in purple line, and actually better than the no assumption IPS. Again, even though the assumption of the cascade behavior is not true. That should be exactly, the strong empirical evidence, in my opinion, that what's important here is not to precisely describe user behavior, right? Rather, we want to optimize the bias variance trade-off or the MSE, right? Bias plus variance. So it's totally okay to somehow or sometimes have this kind of a, intentionally wrong assumption if we can reduce the variance substantially, and also if we can improve the MSE, which is again bias plus variance, right? So, right, the motivation is very different from maybe the user behavior modeling or information retrieval, but rather we can just utilize this kind of behavior assumptions. But our end goal is to design an accurate estimator in terms of MSE. So we sometimes see this kind of very interesting phenomenon. So this is the basics of the behavior modeling approach, right? By combining the behavior modeling knowledge and the policy variation estimator, maybe you can design your own estimator then. Then maybe, right, potentially we can deal with the ranking action spaces by substantially reduce the variance. So seems very interesting, seems very powerful and flexible in general. But of course, right, the existing behavior modeling approach does have some limitations, which I was able to come up with very quickly. So there are three limitations. So one limitation is, so it's actually very difficult to always explain user behavior using only single universal kind of assumption. I mean, independent assumption or cascade assumption. So what I mean by that is, in the previous literature or previous, the estimators like reward interaction IPS, for example, they assume the cascade assumption for every user in the platform, right? Should be a very strong assumption. What I mean by that is the user behavior should be much more diverse or heterogeneous in almost always. So actually, even if we use seemingly reasonable cascade assumption, we end up having a lot of bias by ignoring this kind of possibly heterogeneous user behavior. So that might be one critical point of the existing behavior modeling approach. So another thing is, of course, right, that kind of behavior modeling approach applicable only to the ranking interface or the ranking problem. It's a very specific assumption to the ranking problem. So cannot be applied to different applications, maybe medical applications, I mean, much more general large action spaces. So it seems very interesting, but a very limited application. And finally, which I think is also very critical is, so even the simplest estimator, of course, the VAE-IPS estimator, assuming the independent assumption, still need to address the number of unique actions, maybe unique products or unique movies, which itself is a very likely to be large, right? So what I mean by that is, if the number of unique actions is very large, even if we use a simplest estimator, there's no hope, right? So what the behavior modeling approach is doing is just to make ranking action spaces tractable. So if we cannot utilize any user behavior assumption, I mean, the large number of unique actions, there's no hope. So this limitation actually motivates more recent approaches, which I'm gonna talk about in the rest of the talk, maybe 14 minutes or so. So let me talk about the first topic. I mean, the user behavior is always diverse or heterogeneous in your platform. So we should definitely incorporate this kind of a possibly diverse user behavior in performing policy validation of ranking policies or designing a more appropriate, more useful ranking policy estimator. Okay. So again, to summarize, the idea is it's very possible that different users may follow different user behavior models. So suppose that user A, user B in the platform, and user A might behave in an independent way, but user B might behave in a cascaded way, just very natural setting. But in this case, the problem is neither independent IPS nor reward interaction IPS is optimal, right? So if we apply independent IPS, we definitely have some bias from the second user B, because, right, the independent assumption is not true. But if we apply this reward interaction IPS, then we're gonna have some unnecessary variance from user A, because the cascade assumption is overly general. So we should definitely wanna adaptively maybe switch the importance weighting function for each different user under this kind of a diverse user behavior. So how should we do this? So to think about a possible new estimator for possibly, right, dealing with this kind of a diverse user behavior, let me introduce kind of general formulation of a user behavior matrix. So this is basically very simple, just a generalization of the independent behavior and the cascade behavior. So let me introduce this C matrix. This is just a matrix that represents the possibly complex interactions or user behavior in a ranking. So each element of the matrix is just a binary random variable representing whether the reward at the case position is influenced by the action chosen at another position K prime, right? So this is actually very general formulation of the user behavior, including independent behavior and the cascaded behavior are just special cases. So let me go through the independent behavior and the cascaded behavior and how they can be expressed by this user behavior matrix. So independent behavior is a very simple assumption. So the assumption is the case position is influenced only by the exactly the same position K prime or just a K, right? So this independent behavior should correspond to the identity clique matrix, right? Because again, the case position is influenced only by that case position. So we should be able to express this independent behavior by having this kind of identity clique model matrix or user behavior matrix. We can also very easily express the cascade behavior by having this kind of upper triangular matrix, right? So we need to consider only the top K actions, right? So when we look at the case position, we need to only consider top K actions and also like the top K actions. So that's basically what I'm doing here, just just a general way to express the independent assumption, cascade assumption, and also we can basically express any arbitrary behavior assumption by having this kind of a general framework of our clique behavior, user behavior model matrix. Okay. So one important stuff is given this kind of behavior model and ranking action A, we can actually it's sufficient to condition only on the relevant set of actions when specifying or characterizing the reward distribution or the reward function at the case position. So this is actually also I'm doing just a little bit more general stuff compared to the independent assumption or the cascade assumption. So when we talk about the independent assumption, we focus on the case action when specifying the reward function. We don't need to look at the entire ranking list. When we talk about the cascade assumption, we focus only on the top K actions when specifying the reward function, right? So I'm doing a little bit of a general stuff compared to the independent or cascade assumption. So since we have a general formulation of this clique model, given this clique model, we should be able to focus only on relevant set of action, but relevant set of action might be very different given different clique behavior or user behavior matrix. But just including the independence and the cascade assumption as a special case, we can just focus on the relevant set of actions, just a phi set of actions, this a phi function given this a clique behavior model. So by utilizing the behavior model observations in the log data, we should be able to define actually a more general or possibly dealing with the diverse user behavior. The estimator is a generalized IPS estimator or the GIPS estimator. So here's the definition of the new estimator, the GIPS estimator. It's actually very simple. So what I'm doing here is just to define the importance weight, but differently for each data I, right? So what I'm doing here is just to maybe have this kind of a relevant set of actions to define the importance weight differently for each data I or each user I. So it's very simple. Just go back to the toy example, right? There are two users, user A, user B, and user A might behave in an independent way. So we should definitely apply maybe position level importance weight rather than other types of importance weight. The other user B, might behave in a cascaded way. So we should maybe definitely apply this top K importance weight. So I'm doing exactly that stuff, right? I'm doing just switching the kind of the behavior model given this clique model matrix to define importance weight uniquely for each different user data. So this is what the GIPS estimator is doing, and potentially to deal with diverse user behavior or heterogeneous user behavior. Okay. So of course, there's one assumption when defining this estimator. So I'm now assuming that we observe some user behavior models in the log data, right? So here is maybe the underlying log body data, which is used by this GIPS estimator, or necessarily log body data for making this GIPS estimator really feasible. So I'm now assuming this observation or availability of the user behavior model, which is now sampled from the context-dependent distribution to capture the possible heterogeneity or diverse user behavior. So this assumption is definitely not true, right? We don't always observe this kind of user behavior in the log data. But let me assume this assumption for now because this is very useful to think about this kind of new estimator and analyze this new estimator. And after analyzing this GIPS estimator, I'm gonna definitely deduct this assumption later. So let me just assume this observation was the availability of this user behavior model, which is very useful to think about a new estimator and also analyzing the properties of this GIPS estimator. Okay, so under the observation of the behavior models for now, we can actually have some nice properties of this GIPS, the very general, maybe adaptive IPS estimator compared to the existing estimators. So roughly speaking, this GIPS estimator is unbiased in a much more general setting compared to the existing work. And also we can show kind of the optimality, the minimal variance among the class of all unbiased estimators about this GIPS estimator. So in terms of bias, this GIPS estimator is unbiased given any kind of context-dependent behavior distribution, right? So the expectation is equal to the policy value again. So this actually means that the three-way generalizations provided by this very simple GIPS estimator. So one generalization provided by this GIPS estimator is we now think of arbitrary complex user behavior, right? So of course, including independent behavior and cascade behavior as special cases, but not necessarily the independent or cascade behavior, right? We can actually think of any type of maybe in between the independent and the cascade behavior. We can capture that kind of a very arbitrary complex behavior. And even though we include this kind of arbitrary complex user behavior, we can show that this GIPS estimator is still unbiased. So that's one generalization provided by this GIPS estimator. So any behavior model explained by the matrix can be considered here. And of course, another very critical or crucial generalization we make here is the behavior, user behavior can be context dependent, which we say diverse, right? So since we assume that the user behavior matrix or user behavior model is now sampled from this context dependent distribution, we can actually capture the heterogeneity or diversity in user behavior in the log data, and we still be able to show the unbiasedness of this GIPS estimator, right? So this is also not captured by any existing work in non-game policy variation. And finally, we can show this unbiasedness under the stochastic user behavior, right? So since we are assuming the stochastic distribution among under this for this user behavior matrix, even though we assume this stochastic user behavior, right? User might not realize their behavior in the platform. So maybe it should be natural to assume this kind of a stochastic user behavior. And even though the stochastic user behavior, we can show the unbiasedness of the GIPS estimator. So this GIPS estimator can be unbiased in a much more general setting compared to any existing estimator like independent IPS or reward interaction IPS. And another thing is, right, we can also show the kind of optimality or the variance optimality of the GIPS estimator in the class of all unbiased IPS estimator. So what I mean by that is compared to any arbitrary unbiased estimator in the ranking setting, we can basically show that this GIPS estimator has a lower variance or never worse in terms of the variance. So this kind of minimal variance, I think it's very intuitive because since we adaptively switching or defining the importance value function for each data differently, so there's no unnecessary variance from having an overly general behavior model. So GIPS should be minimal variance, at least in the class of unbiased IPS estimator. So that's basically the idea. So again, the GIPS is unbiased and arbitrary and context dependent and stochastic user behavior, much more general setting compared to any previous work in ranking setting. And also we can show the minimal variance among the class of unbiased or all unbiased estimators. So it seems to be pretty great, right? The statistical properties of the GIPS seems great, right? Unbiased and minimal variance. But of course, one remaining question is we still assuming the availability or the observability of the user behavior model in the log data. And without this observation, we cannot, of course, collectively adaptively switch the importance value function within the definition of the GIPS estimator. So it seems to be a very necessary assumption. So maybe the remaining question to make the GIPS estimator really feasible is, so how should we estimate this user behavior? Maybe using only the available log data. Right, so if we can estimate the user behavior, maybe we can use the estimated user behavior to use this GIPS estimator. But of course, the thing is, it's actually extremely difficult to estimate this kind of user behavior always, right? It's kind of a latent modeling stuff, so it seems very difficult. But actually, here we can maybe go back to the previous discussion a little bit, right? In the previous section, I mean the behavior modeling section, I kind of talk about a very interesting empirical observation where the cascade double reversal or independent, the reward interaction IPS might be better than no assumption IPS or the general IPS, even though the cascade assumption is not true. So that actually implies that actually we don't need to estimate the user behavior in this work. Actually, we wanna, right? It's actually much better to optimize directly the behavior model in a way to minimize MSC. So we now actually not interested in the accurate estimation of the behavior model, but our interest here is to design an accurate estimator in terms of MAC. So again, it is actually, totally okay sometimes to have this kind of wrong assumption if we can reduce the variance substantially or if we can improve the MAC. So maybe we can do the same thing, right? So again, right, it's very difficult to estimate user behavior, but we don't need to actually estimate user behavior, right? We can actually, it should be better to directly optimize the behavior model to improve the MAC. So that may be the better strategy here. So maybe just a little bit of more in-depth discussion here. So the idea is the GIPS with the true model is optimal, but only among the class of unbiased estimators. So outside the class of unbiased estimators or including some biased estimators, that should be much better estimator compared to the GIPS estimator with a true behavior model. So let's just minimize the MSE, or let's just optimize the behavior model in a way to minimize MSE. Might be a wrong model, but we don't care, right? Because our motivation is to design a accurate estimator rather than correctly specifying the behavior model, right? So we talked about this kind of a very interesting empirical results where this kind of a cascade of stuff better than no assumption IPS. Okay. So what I'm going to do here is to optimize some maybe switching function or mapping from the context or user context to a behavior model that could be using the definition or the adaptively defined imbalance function in the definition of the GIPS estimator. Of course, our objective would be some estimate of the MSE or surrogate of the MSE. Of course, this is a kind of an independent topic, right? How to estimate the MSE is also a very difficult problem. There's some discussion in the appendix slides if you're interested. And also there's a very interesting related oral presentation about how to estimate the MSE in the afternoon session. So maybe you are interested in this kind of oral presentation. But assuming that there's some estimate or surrogate of the MSE, again, there's some related work in this how to estimate MSE, which is a more general topic compared to the large scale preservation. So let's assume that there's some useful estimate of the MSE. And what I do here is to optimize some mapping or the function from the context to the behavior model in a way to minimize the MSE of the result in GIPS estimate. Again, we don't care about the correct estimation or the correct specification of the behavior model. That's not our interest. So how can we optimize this kind of a estimate of the MSE in a way to minimize, how can we estimate, how should we optimize or how should we solve this kind of optimization problem? So there seems to be several options how to implement this kind of optimization of the MSE or optimization of the behavior model in a way to minimize MSE. Maybe one starting point or one starting idea would be a optimization of the behavior model based on a subgroup level tree-based greedy optimization. So there are several options. Again, there are lots of future work in this direction, but this is just a starting point. But maybe we can learn some feature partition or the subgroup of the users and the behavior model assignment for each subgroup of the users simultaneously by following the tree-based greedy optimization. So in the decision tree in the supervised machine learning, what we do is to maybe learn the partition of the feature space and a subgroup of the users, and we assign the prediction for each subgroup of the users, right? So we do the similar stuff here. So we learn or we optimize the feature partition or subgroup of the users. What we now assigning is the behavior model for each user subgroup or each partition, feature partition, in a way to minimize MSE. Right, so by just setting the MSE as an objective of this kind of decision making or decision tree process, we can actually very easily implement this kind of the simultaneous optimization of the subgroup of the users and the behavior model assignment. Of course, this is not fully personalized, but one good thing is maybe it's very flexible in the sense that given any surrogate of the MSE, maybe non-differentiable, we can at least implement this kind of greedy optimization of the behavior model assignment and the subgroup of the users. Of course, not better than the fully personalized behavior model assignment, but much better than doing nothing or doing no personalization. Okay, so some preliminary empirical results about this personalized maybe or adaptive force evaluation in the case of diverse user behavior. So there are some baselines, right? IPS and independent IPS and the reward interaction IPS, they are non-personalized, I would say. Estimators, they use only one single assumption for every user. It should be a very strong assumption. So GIPS is kind of a subgroup level, personalized behavior model to minimize MSE. We don't care about the correct, accurate estimation of the behavior model. So we see that there are several types of the diversity in the behavior assumption or behavior distribution, but we see that right, the gray line is the GIPS estimator, and the GIPS enables far more accurate precipitation by correctly optimizing the behavior model by maybe capturing the diversity in the behavior model by maybe using this direct subgroup level model optimization. Of course, this is just a starting point, right? Maybe we argue the problem with the diversity of behavior, which is totally ignored by the existing research. So maybe you wanna develop some more better method on top of this GIPS estimator for better dealing with this diverse user behavior in performing policy separation of ranking policies. But anyway, to summarize the section of policy separation of ranking policies. So policy separation of ranking policies is very practically relevant, but it's extremely difficult because the number of ranking action is exponentially large. So interesting and promising approach in the previous literature is to design some ranking specific estimators by combining a behavior model and a policy simulation. And this is a very highly general setup. So maybe you want to define or design your own estimator, which is specific to your application. But one limitation is they always rely on a single assumption, maybe independent or cascade assumption. obviously producing some bias or unnecessary variance by ignoring the heterogeneity or diversity in user behavior in estimating the policy value. So thus, maybe a very interesting future work is personalizing how to personalize the behavior model assignment to define adaptive kind of importance weighting function. Should be a very interesting and variable direction where estimating the MSE is one of the crucial steps. And again, I want to advertise as a very interesting talk about how to estimate the MSE in the afternoon session. So you should be very interested in this kind of how to estimate the MSE, which is very relevant to estimator selection problem. But anyway, this is the end of the policy evaluation of ranking policies. And finally, let me talk about maybe even more recent topic, which is how to deal with a more general type of large action spaces, and also potentially to deal with a large number of unique number of actions. Okay. So again, I talk about the possibly diverse or possibly heterogeneous user behavior and defining kind of adaptive importance weight. But there are two remaining very critical limitations. One is the behavior modeling approach is very interesting, but very limited application, right? Cannot be applied to different applications. A very ranking specific assumption there. And the other limitation is even the simplest estimator, I mean, independent IPS, still need to address the number of unique actions, which is very likely to be large. And if the number of unique actions is very large, there's no hope. So these limitations actually definitely motivate a development of a more general approach to dealing with large action spaces without assuming any ranking specific estimate, ranking specific assumption. And also we want to potentially deal with a large number of unique actions rather than ranking action spaces. And this is definitely exactly the motivation of our recent work presented at the ACM conference just a couple of months ago. So it should be a very recent topic. But actually, the high-level idea is super simple, very simple. So here is a typical Bundy data, right? Just a collection of context, action, and the reward. One thing I'm going to mention here is I'm assuming the single action policy here, but the number of actions should be very large. Okay, so maybe you can think of it as like a product recommendation thing. And there's some, user context and action choices by a login policy and some reward, just a very basic or very common formulation of the typical Bundy data. But maybe the idea here is, in almost all situations, maybe product recommendations or movie recommendations, we should be able to utilize some more data, right? I mean, the kind of the action embeddings or action features. For example, in this particular setting, item A might be a book category and $20 may be very low price. And the other item B, might be a computer gadget and should be much more expensive, like $500. So the idea is, it's very simple, I think, why not leveraging or using this kind of auxiliary data about the actions in the form of action embeddings or action features should be available almost always, right? Again, the typical one data on policy variation, just a context, action, and reward. This, I think, is not wrong, right? It's a common formulation, obviously. But the thing is, right, they're only action indices, so it should be very difficult, or maybe sometimes overly difficult, to deal with a large action spaces using only action indices, right? There's no similarity information between the actions. But the thing is, right, we very often observe some type of action embeddings or action features, maybe movie category information. So we can actually very easily or very naturally generalize the logomanic data by, assuming the additional observation of the action embeddings, which I'm going to denote by E. So maybe I want to mention that our framework, this framework is very general. So you can basically think of virtually any type of action embeddings. So of course, action embedding can be multi-dimensional, and also can be discrete variable, maybe category information, can be continuous variable, like price information, or maybe you can use some label comments or image data, basically whatever you want as action features or action embeddings, which is available in your application. But anyway, the idea is by not using action embeddings, action features subset. So maybe a little bit more formal, we generalize the typical data changing process by assuming the existence of this type of action embedding distribution. In a general sense, it could be stochastic, right? So given context X and action choice by the login policy, we additionally observe this action features, maybe category information or price information, which is relevant or associated with the chosen action A. So that's basically it. So maybe we can talk about a little bit about the connection between this idea and the online binding literature. So in online binding literature, I think it's a very common idea to assume the feature of the arms or feature of the items, right? There's a kind of linear bundle literature, and it's a very long history there, right? It's a very common idea of assuming this kind of action features or action embeddings in the online bundled optimization stuff. But the thing is, maybe somewhat very surprisingly or maybe weirdly, I would say, this kind of action features, action embeddings idea has never been seriously explored in the evaluation side until 2022, right? But I think the idea itself is very natural, it's very common, at least in the online binding literatures. But why not think of this kind of action feature stuff in the evaluation side? So that's basically the idea. So then the remaining question is, So how should we utilize this kind of action features or action embeddings for achieving much more accurate or much more effective policy validation? Maybe we need to design a new estimator which is able to utilize this type of action feature observations. So by utilizing the action embeddings, action features, we can actually define, again, a very simple estimator of the marginal IPS or the MIPS estimator, which is defined like this. So maybe you can think, or you may think, right, this marginal IPS or the MIPS estimator look very similar or almost the same as the original IPS, just a weighted empirical average of the observed reward, which I think is actually great. Because one thing is, I think anyone can immediately understand what's going on, just a weighted empirical average is the same as the original IPS. And also it should be very easily implementable in any application, right? This is basically the same as the IPS. But of course, there's a crucial difference here, right? The difference is we define the importance weight completely differently compared to the vanilla importance weight. That's a crucial difference, but the only difference. Okay, so since we're doing very simple, it's a very highly general and very easily implementable estimator, we believe. So more specifically, we're defining this kind of, or we're using this kind of marginal distribution of the action embeddings given by or induced by evaluation policy in the numerator and that induced by a login policy in the denominator. So we're doing something similar to the vanilla importance weight, but we focus on the embedded distribution or feature distribution rather than the actual action distribution. So here is a more maybe precise definition of the marginal distribution of action embeddings, doing some marginalization over the action space, just the basic statistical stuff. But often it's useful to provide some simple example to see what I mean by marginal embedded distribution, which actually turned out to be very simple. So there are 4 movies, maybe a very famous or popular movie worldwide, I guess. An arbitrary policy, just a movie recommendation policy, maybe 20%, 10% just stochastic recommendation policy or single action policy. So here's action embeddings. Maybe the simplest example of action embeddings is always category information. Of course, in practice, you can think of a multi-dimensional action embeddings or continuous action embeddings. I mean, this is just the simplest example. So it should be like either a science fiction movie or a sport movie. This is maybe one example of what we mean by action embeddings. And the point of this example setting is, given a policy pi and embedding or category information, the marginal distribution is very easily calculated. Right, so in this particular example, the marginal distribution of the action embeddings, which we use in the MIPS estimator, is just how frequently we observe each movie category, under the policy pi. So definitely depend on policy pi, but in this case, we're gonna observe a science fiction movie 40%, right, 0.2 plus 0.2, and in the remaining 60%, we're gonna observe a sport movie. So this is basically what we mean by marginal embedding distribution. Of course, depend on the policy and how we define action embeddings, but given policy and action embeddings, it's very easily calculated. So it actually turns out that our suggestion or the suggestion of this MIPS estimator is actually very simple. So our suggestion is, let's define the importance weight using the marginal distribution, I mean the movie category distribution, for example, rather than the original action or the movie distribution. That's basically the only modification we're making here. So the basic idea behind this marginal importance weight is we somehow want to ignore the vanilla importance weight, which is definitely the source of high variance. So by doing this kind of marginalization or by defining the importance weight in a different way, we should be able to reduce the variance substantially. So that's basically the intuition of why this estimator seems to be very good. But beyond just intuition, let me go through very briefly the nice properties of this marginal IPS using action features. So roughly speaking, this marginal IPS is unbiased with interesting alternative types of assumptions compared to IPS. And what's crucial about this MIPS estimator is we can actually show that there's a larger variance action for larger action spaces. Definitely very promising when thinking about the large action space policy variation. But anyway, let me talk about the bias first. So under the no direct effect assumption, which is a kind of interesting assumption, which I'm going to describe in detail in a few moments, the MIPS estimator or the marginal IPS is unbiased for any variation policy, satisfying what we call like a common embedding support assumption. So common embedding support assumption is kind of a weaker version of the common support assumption, which requires only the coverage over the embedding space. So we need to care only about the coverage or the common support over the embedding space. I mean the movie category space, much easier than the common support over the original action space. So this is a weaker version of the common support in the sense that the common support, if the common support of IPS is true, then this common embedding support is always true. But the other direction may not always true. So we say this assumption a weaker version of the common support assumption. So which is great, right? Because we're now saying that MIPS estimator is unbiased with a weaker version of the common support assumption. But instead, we have this kind of additional assumption of the no direct effect assumption. So maybe in terms of bias, it's actually very difficult to compare the IPS and a MIPS estimator, right? So in some cases, IPS might be easier to be unbiased, but in some other cases, MIPS estimator might be easier or lower bias because there's a one weak assumption and one additional assumption. But you should be now interested in this no direct effect assumption. So let me be specific about what I mean by this no direct effect assumption. This is also a very simple assumption, but interesting type of assumption about the kind of the quality of the action embeddings. So the no direct effect assumption it actually requires that a given action embeddings, maybe category information, should be informative enough to be able to mediate every causal effect from the action on the reward. Or maybe in other words, there should not be any direct effect from the action on the reward. With that, we call this assumption the no direct effect assumption. Or maybe we can also express this assumption by having this kind of a conditional independence relation among four random variables. So this kind of high level or abstract kind of explanation on this no direct effect assumption. But again, by using some, a concrete example, we realize that this no direct effect assumption is kind of very simple concept. So let's go back to the exactly the same example, right? There are four movies, maybe very popular movies, and exactly the same category information. Just one example of action embeddings, and just an arbitrary expected reward function, maybe conversion rate, for example. And this is actually the situation where the no direct effect assumption is not true, right? What I mean by that is even given, for example, the exactly the same category, maybe given science fiction movie, we see still some difference or variation in the expected reward function. So this actually means that there seems to be some direct effect from the movie on the expected reward, which is not mediated by the category information, or which is not explained by the actual embeddings. So this is actually a situation where the assumption is violated. Or maybe it implies that we need a higher dimensional, maybe two-dimensional, three-dimensional action embeddings to really satisfy the no direct effect assumption. But if if given the category information, maybe science fiction movie, and if there's no difference, no additional difference or variation in the expected reward function, then we can say that the no direct effect assumption is completely true. So I think by using this concrete example, this no direct effect assumption is also just a very simple concept, right? We might have a very informative or sufficiently informative action embeddings to mediate every causal effect from the action on the reward. So again, go back to the bias analysis under the no direct effect. And a weaker version of this common support assumption, I mean the common embedding support assumption, the MIPS estimator is shown to be unbiased. So maybe one thing I want to mention here is MIPS estimator does not sacrifice the nice properties of IPS, right? So this is not better, but not sacrificing the properties. What I mean by that is, right, this is unbiased under one weaker assumption and one additional assumption, so not a stronger assumption. So this is the reason why I'm using the kind of the alternative assumption, right? So the MIPS estimator is unbiased under alternative assumption compared to IPS, different types of assumptions. We of course did analyze the bias of the MIPS estimator under the bias-related assumption. If you're interested in detail, maybe you wanna refer to the paper. But the bottom line is, in terms of bias reduction, or in order to keep the bias small, we need to use kind of an informative action embedding. So action embedding should be as informative possible to keep the bias small, even though we cannot satisfy the no direct effect assumption completely. So that's basically the basic policy or basic strategy we should use, right? We should use maybe informative or higher dimensional, maybe action embeddings in terms of bias. Of course, I'm going to analyze the variance and we're going to have a completely different conclusion, which is a very interesting point of this research. But in terms of bias, we need to use informative or higher dimensional action embeddings. So this is a bias analysis. And let's also talk about the variance analysis. We're going to have actually a larger variance action for larger action spaces, which is a benefit we can get by using action features in policy evaluation. So here I'm doing a very simple stuff again. Just let's take the difference between the variance of the benchmark IPS and that of the MIPS estimator, just to quantify the amount of variance action or the benefit of using action features in terms of efficiency in policy evaluation. Unfortunately, we can get a very simple variance action formula, which consists of the second moment of the reward and the variance of the vanilla bonus rate. So this is a characterization of the amount of variance action we can get by using action features. So it seems to be very desirable, right? So one thing is we see the variance of the vanilla imbalance rate in the characterization of the amount of variance action. So of course, we want this amount of variance action to be larger because this is the benefit we can get by using action features. And we see the variance of the vanilla imbalance rate should be much higher for larger action spaces. So this is the reason why I say that, right, this MIPS estimator is increasingly favorable for large action spaces. We can have a larger variance action, even, especially in many number of actions. So this is the main benefit of using these action features in a way to define the marginal IPS or marginal imbalance rate. But actually, there's another thing. Another thing is a very interesting observation or a very interesting point, maybe from the research perspective, which is, of course, this is the variance of the vanilla input space. But we now realize that this variance is defined with respect to this conditional action distribution given action impedance. So this actually very interestingly implies that in terms of variance, this is actually exactly the opposite compared to what we saw in the bias reduction analysis. But this actually implies that action impedance should not be so informative in terms of variance action. Or maybe this conditional distribution should be stochastic, sufficiently stochastic to get a sufficient amount of variance action. So maybe the brief reason is, so if this conditional distribution is near deterministic, then this variance is going to be closely zero. So we cannot get any variance action by even if we use actual features. So to get a sufficient amount of variance action, we need to keep this conditional action distribution sufficiently stochastic, maybe by intentionally using some noisier or lower dimensional action impedance. So with that, I would say like action impedance should not be so informative in terms of variance action. And what's interesting here is this is again, right? This is exactly the opposite kind of motivation what we had compared to what we had in the bias reduction. So to summarize the point was the bias trade-off of the MIPS better. So to reduce the bias or to be unbiased, we should definitely use informative or maybe high dimensional action impedance, maybe high dimensional high cardinality action impedance to potentially, potentially satisfy this kind of a no direct effect assumption. But to reduce the variance, which is equally important, in terms of MSE, we should actually use coarse or noisy action impedance to keep the conditional distribution sufficiently stochastic. Maybe we should use low dimensional or low cardinality type of action impedance in terms of variance. So one thing we realize right now is the bias variance trade-off of the MIPS value is now controlled by the expressiveness or the quality of the action impedance. So go back to the previous section. We talked that the bias variance trade-off of the ranking specific estimators was controlled by what kind of user behavior assumption we impose when designing a new S-beta. But this time we're talking about this action impedance stuff, and the resulting S-beta of the MIPS S-beta, whose bias variance trade-off is now controlled by what kind, the expressiveness or the quality of the action impedance. So this is the the insight we got from the bias variance analysis, and this actually also implies that there should be a very interesting strategy or practical strategy to actually intentionally violate the no direct effect assumption, maybe by dropping some embedding dimension intentionally to improve the MSE of the MIPS S-beta. So maybe one critical point of the MIPS S-beta is, of course, this no direct effect assumption, which might be unverifiable. But the thing is, this assumption is only necessary for unbiasedness. And again, we care about MSE, and which is bias plus variance. And to reduce the variance from our variance reduction analysis, we realize that maybe we need to, or we should violate the no direct effect assumption by ourselves intentionally. So that may be a very interesting strategy, right? We should sometimes intentionally maybe drop some embedding dimensions, and maybe we should use some lower dimensional action impedance, might improve the MSE of the MIPS better. So actually, we don't need to be overly sensitive to the satisfaction of the no direct effect, but rather we want to control the satisfaction of the no direct effect assumption. So just to summarize the point, the original motivation was, of course, IPS and many other estimators based on IPS become extremely inaccurate with growing number of actions due to the high variance. So maybe the general way to deal with that problem is maybe we can use action features, or maybe why not using action features? And maybe we can develop the MIPS beta based on the no direct effect assumption as a starting point, which is a very simple or very common idea in the online value literature, actually. So we characterize the bias and the variance of the MIPS beta, which implies that there's a very interesting bias variance trade-off in terms of the quality or the expressiveness of the action impedance, which actually also interestingly implies that sometimes we should violate the no direct effect assumption by ourselves, maybe performing some action feature selection for the purpose of policy evaluation to improve the MSE, which is bias plus variance of the MIPS beta. So finally, let me just go through just a few empirical results of the MIPS beta. The left-hand side is the robustness, the growing action set, and the right-hand side is the convergence property of the estimators. So when we look at the left-hand side, with the increasing number of actions, we see, of course, the IPS and W robust may be very inaccurate, so they're very sensitive to the growing number of actions. But we see that, right, this marginal IPS is way much more robust to the growing number of action due to the variance structure property. But what's also nice about this MIPS beta is we can also see the convergence of this MIPS beta. So when we increase sample size, we see that my MIPS beta is getting more and more accurate with increasing sample size. And actually, the thing is, the convergence is much faster than IPS and W robust due to its variance structure. right? So MIPS estimator enables effective polymerization, or at least much better polymerization, or much more accurate polymerization, even in large discrete reduction spaces. And again, the idea is just, why not using actual features in polymerization as well? That's it. So finally, the most interesting result about this MIPS estimator is maybe the robustness to the estimator to the violated assumption. So we test the robustness, or how robust the MIPS is to the violated assumption, I mean the no direct effect assumption. And for this purpose, we synthesize kind of 20-dimension actual impedance, and all 20 dimensions are necessary to satisfy the assumption. So to achieve the robustness, we gradually drop the necessary embedding dimensions out of 20. So in the x-axis this time is the increasing numbers of missing embedding dimensions. So 0 means that we completely satisfy the assumption. So MIPS is totally unbiased. But 18 means that most of the embedding dimensions are missing. So the MIPS estimator should have a lot of bias. And what's really interesting about this empirical result is we see that, right, the MIPS estimator is going to be optimal, or the MSE of the MIPS estimator is minimal if we have some missing embedding dimensions, right? So this actually is a strong empirical evidence that the dropping some embedding dimension intentionally actually minimizes the MSE of the MIPS estimator, even if the no direct effect assumption is not violated, right? It's violated, right? So you don't need to actually overly careful or overly sensitive to the this kind of assumption, but rather you want to maybe think of actual feature selection procedure, for example. That might be a more constructive discussion to make it more practical. So of course, this kind of an interesting phenomenon is completely due to the bias variance trade-off, right? So of course, missing dimension introduces some bias, which is also consistent to our bias analysis. But again, at the same time, right, the variance reduces simultaneously. So we need to care about the bias plus the variance when performing maybe actual feature selection. We don't need to always satisfy the non-direct effect assumption due to this kind of a bias variance trade-off. This MIPS is better. We did discuss very briefly how to maybe perform actual feature selection in our paper, but maybe some future direction there, right? How to optimize actual feature dimension or actual feature embeddings from the data might be a very interesting future direction. So some summary of the empirical result, but I just want to finally mention that what we did is a very simple, right? We just modified the importance weight. So it should be a very promising potential there, in the sense that we can actually simultaneously improve any other estimator that depends on IPS in the polymerization community, right? So since we're doing very simple, we just modify the importance weight. We can just replace the importance weighting part for the marginal importance weight to very easily improve any other existing estimator in polymerization. That's basically the benefit of doing something very simple, very general. Okay, so maybe just a few words about recent relevant feature topics or directions. So maybe obviously, right, we now assume the useful action embedding, the existence of the useful action embedding. So maybe one direction is how to maybe learn or optimize action embeddings or action representation learning from the data for the purpose of policy evaluation or of policy learning. Maybe we want to perform some dimension reduction in a way to retain causal information. And another thing is maybe we want to combine the action embedding approach and also behavior modeling approach to make the policy evaluation of ranking policies much more accurate, right? These ideas are actually now very independent, so maybe we can combine. We can also think of a large-scale policy learning side or offline learning using action embeddings, right? We now focus on the evaluation side. So beyond just evaluation, maybe we can think of a policy learning or policy, offline reinforcement learning using action embedding observations. And finally, right, we should also talk about maybe data-driven hyperparameter tuning or estimator selection procedure for policy evaluation. This is definitely increasingly important for maybe optimizing embeddings and the behavior model. I think right now, again, there's a relevant oral presentation about this estimator selection procedure in the afternoon session. So maybe you should definitely attend that kind of an oral presentation today in the afternoon about estimator selection of policy evaluation. But anyway, that's basically it. Thanks for coming early in the morning. And also sorry for a little bit of a delay, maybe due to the technical issue at the beginning. But again, right, complete slides are available on the website. And also happy to take any questions via email. And also I will be available throughout the workshop day. So I'm very happy to discuss any relevant topic offline. So yeah, happy to take any question and thank you for your attention. Thanks.
Thank you very much, Yuta. Thank you very much. I think if anyone in the audience had a hangover, it should be gone by now. This should have done it. If you have questions for Yuta, you can ask it on the website. I'll also be taking questions in person. If you raise your hand, we may hand you the microphone. Let's.
Yeah, first of all, thank you. That talk was fantastic. That was really great. I just have a quick question about, well, maybe not quick, but a question about the section on ranking. All of these click models make certain assumptions about user behavior, and they're unbiased when those assumptions hold. But are you aware of any analyses that characterize the bias when the assumptions fail, like kind of like what you did for the MIPS estimator?
Yeah, I think the bias analysis is gonna be not so difficult, right? So maybe we can just take the difference of the expectation of the maybe some arbitrary estimator give some wrong behavior model, and maybe you can just compare the expectation and the policy value. But I think they're not paper doing exactly that, right? Basically what the previous papers are doing is just, right, given the real behavior model. So let's assume that every user behave in an independent way, or every user behave in a cascaded way, and then we can be unbiased. That's basically what's done in the previous literature. But of course, right, maybe you can characterize the bias of this estimators with a wrong assumption. Of course, the intuition is if you have an overly simplified or much simpler assumption compared to user behavior, you're gonna definitely have a lot of bias or larger bias. That's basically the intuition. Might not be theoretically innovative, so I may not be so many papers want to analyze the bias analysis, but definitely I think you can do that if you're interested. Yeah.
All right, there's the most voted question right now online is about the propensities. What if they are not available in the logged feedback data, or are very difficult to calculate from the data that's available? How would you handle that situation?
So that might be actually kind of different discussions in the ranking case and the MIPS case, I think. So in the MIPS case, actually, we did discuss a very simple strategy to estimate the marginal importance weight directly. So actually, we don't need to estimate the marginal embedding dispersion one by one, but actually there's a very easy or simple strategy via kind of classification method that we can actually, from the data, we can directly estimate the marginal importance weight, the ratio of the marginal embedding dispersions given evaluation points and log importance. So in the case of MIPS estimator, maybe you want to refer to the subtopic of the paper. There are actually some discussion about how to data-drivenly and directly estimate the importance weight rather than estimating the marginal dispersion one by one. In terms of ranking policies, that might be true, right? Basically, throughout the talk, I'm assuming the availability of the true propensity score in the ranking cases. Might be not so easy to estimate the propensities in the case of ranking policies compared to the single action policies. That's true. So there might be also a future discussion, I think. I'm not aware of any research, particularly talking about how to estimate the propensity scores. In the case of ranking policies, there may be some technically very interesting problem there, I believe. Yeah, so maybe I think that's one additional future direction I maybe should have talked about as well in the future direction, but yeah, very interesting point, I think.
No worries. I mean, there's only so much you can discuss. Thanks for the great answer. We have another question from the audience.
Hello. Thanks very much for your talk. I have a question about the MIPS. So it seems like you assume the embedding is some kind of stochastic, like a probabilistic embedding. But I guess it seems like in practice, it seems more common to have almost like a one-to-one mapping, almost like a deterministic embedding, in which case the MIPS almost, I would say, similar to IPS. So I just want to hear your comments on that.
So that's actually a great point. So this is actually a very general formulation. So one thing I need to mention is, of course, a deterministic embedding is a special case of this typical, our data generation process. So of course, we can capture that kind of deterministic embedding in our framework. So you can, of course, definitely use the deterministic embedding in the MIPS framework. But maybe one example of this kind of stochastic expression is maybe the pricing algorithm. So if you want to define, or if you want to use a pricing information of the actions in the action embedding, that also is very, very possible. And maybe the pricing information might be generated by another pricing or stochastic or personalized pricing algorithm running behind the system, right? So your interest is now is to estimate the performance of a recommendation or product recommendation policy. And one idea is you want to maybe use the price information as one dimension of the action embeddings, but the pricing information might be generated by another independent algorithm running behind the system. And that algorithm might be stochastic and context dependent. That might be a great example of this kind of a more general type of stochastic context dependent as continuous action embedding. So what we are doing here is, right, just capturing any other or any old type of action embeddings we can think of, right? So you can, of course, definitely think of a very simple discrete embedding or deterministic embedding. But of course, we can also think about some example of maybe a pricing algorithm, a continuous and a stochastic and a context dependent embedding. Okay, so maybe another comment would be that, of course, right, in very higher dimensional action embeddings, yeah, that's true, right? MIPS estimator might be the same as the original IPS. That's actually what I talk in the variance and action analysis, right? So if the, the variance, the variance with respect to that conditional embedding distribution is a conditional action distribution is, yeah, this is near deterministic, then we don't have any variance action. That's basically what you were talking about. So that's right. That's basically the reason why I talk about this kind of an interesting strategy to maybe perform some action feature selection. Right. So maybe in some higher dimensional action embeddings, you should definitely perform some action feature selection to minimize MSE. Right. So that might be a very maybe practically interesting. Maybe future work will also be talking about some practical methods for how to perform action feature selection. So maybe in that kind of a extreme higher dimensional case, higher dimensional action embeddings, you should definitely implement some action feature selection. And we talked about one maybe one practical technique for data-driven perform action feature selection in our paper. Yeah, but thanks for the great point.
All right, we're almost out of time, so we have about 2 minutes. So I want to use it to ask you one open-ended question, but I'm going to ask you to not bear in mind that the answer has to be short. I know this is hard for this kind of open-ended question, but it's a very interesting one. So the question is, the number of off-policy evaluation methods is large. Would it be tractable to have an auto machine learning type library in the future that automatically decides which one to apply?
Yeah, I totally agree, right? So maybe a question on the up, right?
Yes.
Actually, I think that talking about maybe auto counterfactual machine learning stuff like that, that would be a very exciting topic, right? So maybe the point is there are many estimators, right? This is maybe the off-policy method. So we don't know ahead of time, right? We don't know which estimator is the best for given programming stuff. Or even in the standard principal setting, maybe IPS might be the best, but WLOS might be the best in some other cases. So yeah, that's exactly true. Of course, right? Then also talk about that kind of estimator abstraction in point simulation later in today. So maybe you should be attending that kind of point simulation or estimator selection problem of point simulation kind of topic. But I totally agree. That's a very difficult problem actually, right? We need to estimate somehow the MSE of a given estimator. But if we somehow could do that, it should be very exciting because we should be able to, we will be able to maybe automatically select the best estimator given the quantity data. That's a very, great situation. So yeah, definitely
let's see.
Difficult, but should be a very exciting future work here.
Maybe if there's a consequences in 5 years, maybe we should check again.
Yeah, definitely.
Thanks a lot for your presentation and for answering our questions. Let's thank Yuta one more time.
Then now it is my great honor to have our next sort of keynote speaker on stage. His name is Lihong Li. Lihong got his PhD from Rutgers University. Since then, he has been a scientist at Yahoo, then Microsoft, then Google, and now he is a senior sort of principal scientist for sort of Amazon. I'm sure many of you will know him, maybe not by name, but you will know the replay, which is a very famous method for doing sort of unbiased offline evaluation. Many of you will have used sort of LinUCB and all of these things, which were all terms that were sort of coined by Lihong. So I'm very, very happy to have him on stage. Please join me in welcoming Lihong, and the floor is yours.
Okay, good morning. Yeah, thanks, Olivier, for the really nice introduction. And thanks for coming to the talk. It's really my pleasure to join this crowd to share some of our thinking and work on this important topic of recommendation and in reinforcement learning. Please feel free to stop me if you have any question during my talk, and we'll also have time for discussion at the end. Okay, so let me start the talk. in recent years, there has been a growing trend of modeling recommendation problem as the decision-making process. For example, in Amazon.com, when you recommend products or music or video to customers, what we observe from the eyes of the website is that we observe the context of the customer and then recommend the content, right? That's what content we're going to show and how we're going to show the content to the user. And then we observe customer engagement signals, and from the signals, we can derive utility or reward, some real number that characterizes how good the recommendation is. And the goal here is to optimize the recommendation policy so that the reward is maximized, okay? And there are many other examples like news recommendation and video, movie, etc. So you can see a lot of application in RecSys in recent years and also in the workshop. And for decision making, one of the powerful frameworks is reinforcement learning. It's a machine learning paradigm that allows the agent to learn from his past experience by interacting with the environment, and through the process, improve his decision-making policy or action selection policy to maximize reward. And there are many examples, right, in this process where we have an agent, like the robot in the figure on the left, interacting with the external environment, the world. And then, for example, what we have discussed, recommendation, also other applications on the web like advertising, search, and robotics, games, etc. And so this is the interaction between recommendation and reinforcement learning. And now the question is, when we try to apply reinforcement learning to build a recommender system or to optimize it, what we're going to do? And interestingly, in a simplified view, the process is not that different from supervised learning, right? Typically, we start from a formulation of the problem, finding the right setup and the right algorithm, and then we collect the data, train the model, and test the model. So we have this 4 steps, very similar to a supervised learning application. Except here that in reinforcement learning, all 4 steps are more complex or trickier than supervised learning. For example, in formulation, we have to specify what the state, reward, and action are, and there are many variants in this formulation. We're going to see some of the examples soon. And for data collection, there is a need to do an exploration, etc. And even for evaluation, that seems simple. There are a lot of hard technical research questions to be addressed. We see some of these examples in the rest of the talk. Okay, so let me start with the first step, the formulation, and then I'll talk about exploration and training because these two are typically coupled together. So I'll put them together, and then I'll focus more on the last part, off-policy evaluation, which is to evaluate how good the policy is. This corresponds to the last step of these 4 components. Okay, let me start with the formulation. So I guess that people are really familiar with this formulation of MVP, where we have just a fixed notation. We have the set of states S, set of actions A, and T is the transition function. What's the next state? What's the probability of landing in the next state given the current state and action? So that's what T is. And reward function is the 1 step or immediate reward function, the short-term reward function. And mu0 is the initial state of the system. Gamma is the discount factor, typically between 0 and 1, less than 1. It can be when it's 0, and when the and so that's the MDP. And then we have a special case, important special case called contextual bandits, where the transition to the next stage do not depend on the previous stage or actions. So that's why in this case, we have states that are sample IID from a fixed distribution. And that simplifies a lot of things in algorithmic design and experiments. So this is the basic setting. And in practice, let's say we try to apply this formulation, say the simpler bandit formulation to a video recommendation problem. So on the left-hand side, you see that we have 5 candidate videos to recommend to a user. And what we try to maximize here, the reward function, is defined as one when the customer clicks on the video and watch this video. Okay, so it's a binary reward. And in this case, this is a very basic and popular formulation. Okay? And then there are many algorithms for solving this problem. For example, you can use a generalized linear model inside Thompson sampling to do an exploration, and then use the linear model, the generalized linear model, to predict the view-through rate, the probability that the customer is going to click on a video and watch it. And then you use Thompson sampling to balance exploration and exploitation. So in this case, we start from an uncertain value of the weights in the linear model, described by the flat distribution of the weights. Okay? And then as time goes on, when we collect more and more data, the posterior distribution of the weights in the linear model concentrates, and then we can do less exploration. That's how Thompson sampling works. And suppose that now instead of trying to maximize the number of clicks, now we say we'll want to maximize the time the user spends on watching the video, then the reward function becomes real value number. And then we could simply change the linear model to another model that can capture real value reward. This seems simple. But then let's say we want more variance. For example, instead of recommending one action or one video to the user, we can recommend a subset, right? A subset of videos or a ranked list of videos. Or maybe we can optimize the whole page content, the font size, layout, etc. on the page. Or even we want to maximize multiple objectives at the same time, right? Not just click-through rate, but also the time to watch, and also other metrics that we think are important to measure user satisfaction. So we can have multiple objectives, and all these correspond to different settings in reinforcement learning. And that's why there's a huge literature on bandits and reinforcement learning. Even for the simpler bandits, if you go to Wikipedia, you can see a lot of literature. And recently there are 4 books and even more. I think there are more books on bandits. So the question here is that the rich literature offers a rich set of toolbox, but at the same time, it's hard for practitioners to find the right solution, right, for the problems. And that's why we need a map to help practitioners to define the right setup and starting point to develop an algorithm. And that's why we in the last year, we have a short paper describing a map for a first map of bandits for e-commerce problem, but some of the thinkings can be used in other applications. To give an example, we could group bandit algorithms or problems by the properties of the reward function. And you can see that in this map, we have identified 10 most popular characteristics or properties of the reward function. Right? It could be scalar, it can be multi-objective versus a single objective, and the reward distribution can be adversarial, stochastic, etc. And I should say that this map is not exhaustive, but at least it gives a reasonable way to group the literature into subsets so that it's easier for people to find a useful setting. As an example, let's look at the node 4. The way we do it is that use the map is that we could see whether the reward function is a single scalar or multi-objective. For example, in video recommendation, we want to maximize click and time at the same time. We will go through this route. And then it will also have, if one of the reward is what we really want to maximize and the other dimension rewards are constraints, then we can go to the lower path, which correspond to 4. And then in the paper, you see there's a table where you can see that in 4 here are 1 or 2 representative reference for that problem. And hopefully this would provide a useful resource for practitioners to find a good setup for RL in the problem. We also talk about grouping the literature by action properties like type and size. And for details, if you're interested in the details, the paper is available online. Okay. So the first one just gives to give you a basic some idea of how we may formulate a problem as reinforcement learning. In recommendation, we can have different variants. I think that so once we have the formulation fixed, then we can talk about data collection, meaning exploration and training. Okay. And then in exploration, there is in RL, there is a standard need for trading off exploration and exploitation. And there are many ways to do exploration. For this crowd, and I think that the crowd here is familiar with this literature, so I'm going to skim most of the slides, except that I just want to mention that many of the existing approaches are based on simple models. For example, linear models, where it's easy to develop a closed form or tractable approximation to measure the uncertainty of the prediction, right? For example, in the Thompson sampling example earlier, we used a generalized linear model when the posterior distribution can be easily approximated. Now, when we go to more complex models like neural network models, it's not easy to compute the uncertainty in an efficient way. So how can we do this? By taking advantage of deep learning models. And here are two recent examples from previous work, neural, where we incorporate neural networks into UCB and Thompson sampling exploration strategies. For example, in Thompson sampling, this is the new version of Thompson sampling. We can use a network that is a standard feed-forward neural network of L layers and M nodes per layer. And all the parameters theta is the parameters of the network, meaning the weights of the neural networks. Okay. And then the structure of the algorithm is very similar to standard Thompson sampling, except for a few changes that I highlight here. The first is that we need to initialize the weights of the neural network with a Gaussian. That's for technical reasons. And then we compute the covariance matrix. Initialize the matrix with the scaled identity matrix. And then as similar to Thompson sampling, we sample reward from the posterior. The details will be in the next slide. And then we sample the reward from this posterior distribution and pick the one that looks highest in this sample. And then we use the observed context and reward pair to train the network model. And finally, we use the gradient of the neural network to update the covariance matrix. Here, this is just a gradient, so you can compute it easily with backprop and do this calculation updates efficiently. Okay. Now, the key part here when we do Thompson sampling with the neural network is how we can define compute the posterior so that it's a principal and sound method. The way we do it is this. We approximate the posterior with the Gaussian distribution. The mean of the reward for an action A given a context X is this. It's just the outputs of the neural network according to the current weight. So that's simple. Now, for variance, we could use the gradient of the current context and the dot product of the gradient with the covariance matrix inside to compute a variance. So if you look at the form, it's very similar to linear models like linear UCB. The technical challenge here is that how can we ensure that this is a valid covariance matrix in neural networks? And there's a lot of details going in the paper, but at the end of the day, the message is that this covariance matrix is a sound method. You can use it to guide exploration effectively. In fact, there's a theorem that says that under typical technical assumptions, right? And then when the parameters are appropriate, neural Thompson sampling can approach a regret that's comparable to previous work. There are some technical details here. If you're interested, you feel free to ask the questions offline or get the paper, read the paper, which is, I think it's in iClear last year. Okay. And then these are the some of the examples of neural Thompson sampling compared to a number of baselines like linear UCB, linear Thompson sampling, and kernel versions, and bootstrap and epsilon greedy. You can see that neural Thompson sampling, the red one, has the lowest regret compared to others as time goes on. And then if we we also look at the impact of update delay on Thompson sampling compared to the new version of UCB, and we see that it's more stable than UCB. And this is one of the benefits of doing Thompson sampling is the updates is stochastic, so it doesn't have to. It's more robust to delay in the updates. Okay. So far have talked about how to formulate the problem, how to do exploration to collect data, and how we could update the model with neural networks, train a model. And in the literature, when you model the problem as a MDP for optimizing long-term rewards, you can use other algorithms like DQN or actor critic, etc. And there are a lot of work recently to use these methods to maximize long-term rewards, right, or session rewards for recommendation system. And next, I'm going to focus more, and for the rest of the talk, I'm going to focus more on the policy evaluation, as this is, I think this is one of the most important, most interesting topics of this workshop. Again, this is the the notation of MDP. Again, we have the states and action transition reward. So these are standard notation. And then when we start from an initial state of an MDP, for example, we start from an initial state of the shop of the customer when we recommend videos to or items to the customer, the initial state of the customer as 0. Then we follow some policy, some recommendation policy, and recommend a content. Content here is A. And after consuming the content or seeing the content, the user moves to the next state with a reward, and then we can repeat the process. This is how we generalize a trajectory in the recommender system. Right? This is a Markov process. The U function here is the return in the reinforcement learning language, which is the cumulative reward of the trajectory. It's a random variable, and in reality, when we care about is the average of the return, which I call the policy value here, V of pi. So this is the average reward of the running the policy. For example, if you define the reward as the time to watch the video in a session, and then the policy value V pi is the average time of watching the video in a session of the, depending on how you define a session, a sequence of actions for the customer. Okay. And this is the quantity we try to estimate, right, the policy value. And then there are different ways to estimate the quantity. The most natural way is to do an experiment. We can run online experiments and observe how the policy works, how well it works on real customers, and collect the data. And compare to a baseline. This is the A/B test in the industry, and very popular and statistically sound, and there's a very transparent and straightforward method. This is great. On the other hand, it's costly. It takes time and efforts to do these experiments. We can't always do a lot of experiments because number of users is small and number of the traffic is limited. In some cases, we can't even do that, like healthcare or autonomous driving, where the cost of making a mistake is high. The other approach is called off-policy evaluation, where instead of running experiments on real user, we assume that we have access to historical data that was collected by a different policy. For example, a previous version of a product policy. Okay, we have access to this data, and then we estimate the same quantity from the data. Now, the benefits of this approach is that it's easy, it's cheap. It's not easy, but it's cheap, it's safe. Okay, but the challenges here is that we don't observe the reward of a different policy when the different policy recommends a different action than the one in the data. So this is the bias problem, because when we average reward in the data, what you get is the reward of the old policy, not the policy you care about. See? And fundamentally, this is a counterfactual estimation problem where you want to use data in the past to predict what could have happened if you switch the policy from the old one to the new one. Okay? And that's why there's a lot of connection to causal inference and counterfactual estimation. Yeah. And one of the approaches, I think, which is also very popular and one of the first approaches people may try, is to build a simulator. It's very, for example, in games, the simulator is almost perfect because the game is a simulator itself. In robotics, we can build a good simulator based on our understanding of the physical law. Okay, so in many cases, we can still build reasonable simulators. But as the complexity of the problem goes on, for example, when to build a user click model, when we build a customer behavior model, or even the healthcare patient medical model, it becomes more and more complex. And so even though simulators can be a very powerful tool, in practice, it can be hard, it can be very challenging to build reliable simulator. And that's why in this talk, we focus on the different approach that does not depend on the simulator, but depending on the historical data itself. Okay. And then I think that in this morning, the tutorial this morning gave a really nice introduction to a lot of these techniques. So I'm going to skim the basic techniques by just quickly and okay. So here, remember that we are talking about estimating the long-term reward, and the data is in the form of trajectories. Right? We see a user A and a sequence of recommendation to the user and the corresponding responses from the user in a session or in a trajectory. And then this data again is generated by following a behavior recommenders policy pi0, and now we want to estimate the policy value for the policy that we are interested in. And when the behavior policy pi0 is not known, we call it behavior agnostic OPE. It's a more general setting. And in some cases, we'll see soon that sometimes you don't really need to know the behavior policy. Even you know it, in fact, there is research that shows that even if you know the behavior policy, sometimes it's better, statistically better, not to use the information, but rely on the data to estimate it. Okay. Okay, and then in reinforcement learning, and MDP and reinforcement learning, we have when we talk about the reward, the long-term reward, and we need to talk about something like the value function, which is also a standard notation. So just fix the notation here. Is called a Q function, which is the expected long-term reward if you follow a certain policy from a first state and the first action. Okay. And then the important fact about the value function is that it satisfies something called Bellman equation. It's what it says is it's a very intuitive equation that says that the long-term reward you're going to get from this state is the same as the one-step reward plus future state you're going to get from the next state on. So this is the principle according to the principle of dynamic programming. But this simple equation is the backbone of a lot of the algorithms to compute the value function. Okay. Okay. So now with all this notation, now we can talk about how we can estimate the long-term value of a policy. The first one is called the regression estimator or plug-in estimator. What we do is that we can use the data, the trajectory data, to estimate the transition of reward function of the MVP. Right? We don't know how the user is going to do, but we can estimate the behavior and state transition from data, and pretend that this model we estimate from data is the real model, and we compute a value function, and from the value function we can get a policy value directly. We can read off from the Q function in the first state and first action. This is very simple in an approach, and is the variance is typically low. But the tricky thing here is that when we estimate the Q function, when we estimate the transitional reward function in large state problems, we typically have to use some kind of assumption, some modeling assumption to make possible. And this kind of assumption will introduce bias or error, estimation error in the model. So even if you have a lot of data, you can never be sure that the model you build, the transitional reward model, are accurate. So there's this uncontrolled error part that makes it hard to interpret the evaluation result. Another way, which is more transparent, is the IPS approach, inverse propensity score. The idea is based on importance sampling. I think that this is very similar to what we saw in the morning tutorial, except here that we have to write down the ratio, the propensity score, into a sum of the transition probability and actions for the certain steps. The reason we can break down is that it's a Markov process, so we can factor the whole probability of seeing a trajectory into small probabilities and individual time steps. Okay. And the good thing about this is that a lot of the terms are canceled, the terms that we don't know, the transition probabilities. So what we end up with in the propensity score is the ratio of the policy of individual steps and multiply together. And that's the propensity score for the whole trajectory. Okay. And then we can use the importance sampling or importance weighting to get an unbiased estimate of the policy value. Now, although the estimator has zero bias, unbiased in principle, mathematically, but the problem is that this approach usually have high variance. To see this, if one of the probability pi 0 is very small and the corresponding pi is high, the ratio is large. So small variation or noise in U will be magnified by this ratio, and that's why we have a lot of high variance in this estimator. And there are many variants of this basic IPS approach to reduce the variance. Here's a few examples, or I'm sure there are more recent examples. Unfortunately, this approach IPS is not widely used when we talk about long-term rewards, or equivalently when the discount factor gamma is close to 1. Remember that the discount factor controls how fast future reward decays. If gamma is close to 1, that means that we need to have a good estimate of future reward. And that's why we have to estimate the importance ratio of the future states accurately. And then in this case, this estimator IPS has really, really large variance, as I'm going to show in the next slide. It's a phenomenon that we call the curse of horizon. To look at this, if you look at the ratio, the product of ratios of the trajectory, each term is a random variable, right? Pi over pi 0, it has variance. Now we are multiplying several of them, each of them, and each of them has a variance, and multiplying them has, typically you can end up with an exponential blow up in the variance of the final ratio. Okay. And in fact, we show that this exponential ratio cannot be avoided in the worst case. So that seems like a piece of bad news. However, the question is that in practice, not all problems are that hard. For some problems, because of various reasons, maybe we don't have to do it this way. And maybe the problem is easier so that we can avoid a curse of horizon. And that's what I'm going to show in the next few slides. And so next, I'm going to talk about an algorithm which was published about 3 years ago called do-dice. It's a method for estimating the long-term rewards without having to do this ratio, to compute this ratio along the trajectory, and therefore possibly avoiding the exponential blow up in variance when the problem is benign. And notice that I haven't defined what benign is, but I'm happy to talk more at the end of the talk. Okay, so what do-dice works? How do-dice work is as follows. It doesn't it doesn't need the data to be in the form of trajectories. In fact, it's very flexible. It just assumes that you have a set of transitions: previous state, previous reward, next state, and reward. So the tuple, right? You have a set of n tuples, and the state action is sampled from some unknown distribution, right? Depending on your data collection process. Maybe it's collected from one of the production policies in the past or several of the policies in the past. It doesn't matter. And then reward and next states are sampled from the MDP itself. Okay. And then what DuDice DuDice is based on the key formulation of here. In MDP, a market decision process, when we try to solve the value function, people here may be familiar that we can use value iteration, or policy iteration, or DQ, and things like that. Okay, so that's one way to do it based on the Bellman equation. There's also another way to get the value function using linear program. And this is the linear program of writing down the value function for the MDP. What it says is that this is the average. So here, in the linear program, the variable is Q, the Q function, okay? And we want to minimize the Q function when it's evaluated on the initial states and actions, and then we want a linear constraint when Q is bigger than the reward function plus the future expected value measured by Q. So this, you may realize that the constraints are very similar to the Bellman equation. Okay? In Bellman equation, what we have here is the equal sign, but here is bigger than equal to. And you can see, you can show that if the Q function satisfy this inequality, the Q function is an upper bound of the true Q function. Okay? And then by minimizing this Q function, we're pushing the Q function to the true Q function. And that's why when you solve this linear program, the resulting Q function is the true Q function, and that's why you can get the policy value from this LP. Okay? So this is the typical way of writing down the LP to solve an MDP. Now what DuDice does is to look at the dual version of the LP. So converting from the prime to dual to standard, the standard operation in LP, where now the objective function becomes the reward function, and the constraints become a linear constraint of equality constraints. Okay. So let me talk about this constraint first. This constraint may look mystical, but in fact has a very natural meaning. It's a distribution over state actions. And then what the equality constraint says that this D satisfies a certain equilibrium condition. If you sample a state action from D in a certain time steps, it's the same as sampling state action from the initial state distribution, or sampling the SA from the same distribution but but going backward one more step, one time step. Okay. The key operator here, P star, is the adjoint operator of the previous P. So you can think of it as a going back in time. In the primal LP, this is the transition probability of going forward one step in time. This is going backwards. So what it means is that if you look at the distribution of state action in T versus T minus 1, the distribution is the same, right? Up to a certain adjustment with the initial state distribution because of because of the discounting. Okay, so the reason we look at this dual LP is that it offers us a way to look at the distribution of states without having to look at the distribution of trajectories. Okay. in the past, if you remember in the IP, the basic version of IPS, we are talking about trajectories as a unit of data points and talk about propensity score of the unit. Now, we turn the unit from a trajectory to a state action pair, which is a fixed set of objects. We don't have to worry about how long the trajectory is, right? So that provides a possibility to avoid the curse of horizon, the exponential blow up. So how are we going to use this equation to do this? So the idea is very simple. The basic idea is very simple. We want to find a distribution D over state actions that satisfy this equality constraint. So what we do is to model. What we do is to compute the importance ratio or propensity score of this D over the data distribution. Right? Because once you can do this, then you can apply this importance weights to reweight data you have in the data set. And the data set is drawn from the data distribution. And after reweighting, you can debias the data so that your data set is effectively generated from D sub pi. And D sub pi is the unique solution that satisfies the equality constraint. Okay. So instead of looking at the trajectory importance sampling, now we can look at this importance ratio of the state action pair. Okay. Now, how do we estimate this? Again, even with this importance ratio, the equality is still the constraint is still equality constraint. Although the dimension could be high or even infinite if the number of stages is larger infinite. But fortunately, we can use parametric model or non-parametric models like neural networks to model this importance ratio zeta, this zeta quantity. And then we can define an objective function that measures we can define an objective function that measures the discrepancy between the left-hand side and the right-hand side of the equality constraint. Okay? And this is the basic idea of DUDICE. We define a discrepancy function that minimizes the difference between the two sides of the equality constraint. And by minimizing the model in zeta, then we can compute zeta in a scalable and efficient way. Okay? And once we have the zeta, remember that this is the importance ratio. All we need to do is to use zeta to reweight rewards in the data, and the average reward will be your policy value. Okay. And then this approach is it's sound. We develop conversions and other properties of these methods, and there's a lot of variations, such as how to make it into a double robust and how to compute confidence interval, and also how to handle unobserved confounding in special cases. Okay. And then let me skip these results. These are all from the paper in the NeurIPS paper, which show that DUDICE can reliably give you good results compared to basic IPS or other methods. Okay, so now in the rest of the next few minutes, let me quickly go through a recent work we did, how to handle non-stationary problems. And this is joint work with colleagues, including Ziyang sitting over there, and it was also presented in the industry track a few days ago in RecSys. And we have a full paper upcoming soon. So if you look at the setting that we study OPE is based on MDP, okay? And one of the key assumptions in MDP is that everything is stationary, reward and transition. But this is not true in many recommendation problems. For example, customers may want to watch more movies in the evening than in the morning. Okay? Or on prime days, customers tend to shop more than other days. Okay? And so these are the examples of non-stationary signals from customer engagement. However, if you look at the relative metrics between two policies in this plot, we show the difference. Well, we show two business metrics between two groups of users. One group of users is exposed to a control policy, the other is exposed to a treatment policy. You see that there's a lot of variation in the metric, but the difference between the two treatments is relatively stable. So that motivates us a modeling assumption of the non-stationary problem, where this is the model, OT equals ST plus CT. And OT is what we observed about the user engagement, like visits, clicks, and purchases. And ST is the unobserved state variable of the user, model is in state of the MTP. And ST is we assume that ST is stationary, okay, like a typical MTP. And then ZT is the corresponding noise that comes from the exogenous factors, like seasonal effects, and is independent of the treatment we apply to the customers. Yeah. Okay, now under this model, how can we do OP? How do we estimate the long-term value of the policy? Here's what we did in the paper. First, we consider a simplifier setting where we use a linear model for a linear assumption on the transition model and the reward function. Okay. And for this special case, the dual dice algorithm will give you a nice closed form solution that you can easily calculate. Okay. And then everything here is fine. And you can estimate the value of a policy using dual dice in closed form, and you can apply the same estimator to the control policy and the treatment policy. And the difference here, delta hat, will be the estimate of the treatment effect, long-term treatment effect. Okay. So this is the standard setting when we don't assume non-stationary problem. Now when we have the exogenous noise, what we can do is to design a objective function that try to learn the transition function. This is for treatment. This is for control. The transition function for control, transition function for treatment, and ZT are the exogenous noise that we try to model, and these are data set. Okay, the first three are the parameters where we try to optimize in this objective function. And what the objective function does is to minimize this error. This error has the meaning that if O is the observed state minus ZT, that will be the unobserved state, real state that is stationary. Okay, and this real state should satisfy the linear transition model, because that's what our linear assumption is about. So by optimizing the 2M matrix and ZT simultaneously in this objective function, we can estimate the noise and estimate the transition model in the same place. And for optimizing, we can use alternating minimization that is easy and to do in this linear model. And when we apply this method on synthetic data where the state is a Markov process and noises are artificially generated and added to the state, you can see that as the number of trajectories increases, our method, the green one, you reliably get to the true error. The error is the error goes to 0. There's a log error. And the naive average, which does not consider which used short-term measurement to estimate long-term effects, it has a high bias. And the other one that does not consider the noise, the time varying exogenous noise, has a higher error. And then if you vary the degree of non-stationary, the alpha parameter here to control how big the noise is, you can see that as noise goes up, is more and more the error produced by stationary estimator OPE will give you a higher error, which is expected. But our method, the green one, is very robust to the noise. So this is a synthetic result. We also tried on the online stored data in a 12-week experiment. We used the first 5 weeks for estimating using the estimator, and then the last 7 weeks for validation. We use the observed 7-week result as the ground truth for long-term effect. And then you can compare naive average, stationary, and non-stationary. We see that although this is just a single experiment, we see that the OPE methods gives you promising results compared to naive average. And we have done more experiments afterwards, and we are hoping to have more to share in the full paper that's coming up soon. Okay. So today we look at the recommendation problems and also talk about how we can look at this building a recommenders system from an OIL perspective, from formulation to data collection to training and testing. Okay? And then there are many interesting and technical challenges to tackle, and many of them are the topics of active research these days. For example, how can we handle large state actions? I think there's some really interesting work at ICML this year. Also, how we can deal with non-stationary problems. The example I showed just now is based on a basic model, but how do we handle more general non-stationary problems for other scenarios? And also, a very interesting question is that when we recommend to customers and the customers interact with each other, we can't treat them as independent units because of social effects or other effects. How can we think about recommendation when we know that there's some interaction among customers? I think these are some of the interesting questions, and I'm happy to stop here and take questions. Thank you.
All right. Okay, great. We can take some in-person questions if anyone wants to ask one. If not, I will go through the one on the website first. So the one that is most voted right now is whether you feel that using neural TS is scalable and feasible in large-scale real-world systems. And I think the main reason for this question will be, the fact that you now have this whole matrix for the covariances. I guess when your neural net becomes really large, that matrix will become really large. And so I guess both the gradient updates and the sort of model inference might become much more complex.
Yeah, sure. If I understand the question, the scalability is, the question on scalability is on the number of actions or the number of the size of the model?
That is a good question. It might be both. Yeah.
They're both okay. Yeah. I think the different ways to tackle this for the scalability problem. When the number of actions is big, I think this is one of the active research questions. There are different ways to handle it, like embedding or doing some multi-tier way to select items. You select a small set from a large set using some lightweight method, and then do more complicated things in later pipelines. So when the number of actions is large, I think there are different ways to handle scalability. When the model is large, I think that's I don't think that's maybe it's a problem, but if you think of many of the current neural recommender systems, they're using neural network to do the recommendation. And then when if you look at the way we do the exploration and neural version of Thompson sampling, the most computation expensive part is in calculating the covariance. I think that part also has other ways to reduce the complexity. For example, I think in the paper we experimented with an approximation that only look at the diagonals. So that will reduce the time from quadratic to linear. And then there are many other things that we can other tricks too we can use to scale up the methods.
Right. Okay. I will assume that has sort of been a really good answer to the first question. A second question that we have is whether you could talk about use cases for reinforcement learning in ads.
In ads. Yeah. So for use, I think there are I'm talking about general terms. I think when you look at ads, in a sense, we're also showing contents, right, to user based on the query or the context of the page. So a lot of the things we saw in recommender system also have similar problems. And as for example, how we could show what ads we can show and how we can trade off exploitation and on the advertiser side, we can also think about, for example, how we can do online learning exploitation on behalf of advertisers, things like that.
Right. Yeah. Okay. Do we have any sort of in-person questions? No. We do. Okay.
Hey, Lihong, thanks for the talk. My question was also on neural Thomson sampling. I wonder if you have any commentary on the computational as well as the practical performance comparison between neural Thomson sampling and approaches that use bootstrap, like ensemble sampling, and more recently the epistemic neural nets, both from a computational standpoint as well as practical performance.
Yeah, so in the experiment did it's on the small scale examples, small scale data sets. So for large scale comparison, I don't have the results I can share. I think it's an important thing to look at. But if you compare the neural Thomson sampling with bootstrap, I think there is a possible benefit that we don't have to train and infer on multiple models simultaneously. Okay. And then we can only just use one model. And also, I should also add that the way we do the neural Thomson sampling is just one way to do it, right? And some of the decision is for convenience in mathematical analysis. But in practice, there are many ways to do neural Thomson sampling. For example, we could do typical standard neural net training for the weights, and when you do an exploration, we freeze all the previous layers and only explore the last layer, and then we convert it to the problem to something very similar to linear version. Okay. And the first few layers are feature extraction, the last layer for the linear model for exploration. So there are different ways to scale this up.
Right. Okay. Let me move on here.
Hi, a great presentation. Thank you. Evaluating reinforcement learning-based solutions has a lot of pieces, let's say, and reproducing existing publications is a challenge many times. Which are like the biggest, let's say, challenges that you see in reproducing existing works, and if you have any suggestions for the community to maybe solve some reproducibility challenges in evaluating these approaches? I was hoping you could talk a little more of that.
Sure. Yeah, so I think there are many challenges when we apply this always. I think I can think of a few. For example, in formulation, the most popular setting are MDP and sometimes contextual bandits. But when you apply it to a realistic problem, a real problem, there are many other constraints that may make the algorithms not suitable. Right? To give an example, for example, in some problems, right, when you recommend an action, it comes with a cost. We can't always select a certain action all the time because we have a certain budget of taking a certain action, right? For in recommendation, maybe you want to ensure that all contents cannot dominate all the recommendations. So there's a budget, something like that. I'm just making up an example. And in this case, you can't just apply the standard methods and expect it to work. And there are many variations that have these subtle and important differences. And that's why I think formulation is one of the things that are important first step. And also, when you think about reward, here rewards are typically stationary, right? There's some fixed reward function to try to optimize in bandits or in RL in general, but in many problems, it's non-stationary, and also when customers interact, you lose that kind of independent assumption. So that complicates things a lot. And so I think that's and also you can't do experiments easily. And that's why policy evaluation from data is so important in practice.
Okay, we have time for one last question.
Hi. I have a question about your dual dice. When you're developing that algorithm about algorithm, did you have a vision, like the macro vision about like future computational power? Like when I say this algorithm, I say that it's paying cost by computational power, right? So when you are like when you apply this algorithm to the data you will have, like Amazon data like that, like is it like in the future it'll be like scalable? You thought like that?
Okay, sorry, I'm not sure if I get all the questions. Is it? Yeah.
Oh, so I thought that like
mic is not working.
Yeah.
Well.
I thought that the dual dice is actually paying like computational cost, right? Like it has the linear program, like a cost, right? It's a state action pair size big, like computation, right? So I was thinking like when you're developing this algorithm for the real world data application, you had a vision that like in the future, the computational power will be like a big or something like that, or
Is it about the OPE part? Yeah. The feature, the solving the linear constraint. Yeah. So when the scale again about scalability, right? There are different ways to do this. As mentioned in the talk, you could have, even though the number of constraints is large, and you could have a model, a neural net model, or some other model, right, where the input is the state and output is zeta, the importance ratio, and then you have a limited number of parameters to learn as opposed to maintaining a number for different state action pairs. If that's what, and then you can optimize the neural network model from data, like supervised learning, the typical deep learning applications. And is that, I hope that
right.
answers the question.
Okay, we will need to move on, but Lihong will be around. So I'm sure you can grab him by the arm if you have more questions later. So let's please all thank Lihong again.
Thank you.
And then next up, we have two very interesting papers. First one will be presented by Alexander Buchholz. This is work he did with Ben London, Giuseppe Benedetto, and Thorsten Joachims. And it's going to be very, sorry. And the main topic will be very much in line with the first half of our day. It's about using sort of off-policy evaluation in learning to rank. The floor is yours, Alexander.
Thank you very much for the introduction, Olivier. Okay, so yeah, hi, I'm Alex. I'm an applied scientist with Amazon Music. And the work that I'm presenting today is about how to do off-policy evaluation for learning to rank by interpolating the item position model and the position-based model. So I'm going to quickly motivate our work by giving you a glimpse at ranking at Amazon Music. So this here looks, this is what you see when you open the Amazon Music app. So this is the landing page we call Browse Home. And here you see different categories that we call widgets. And these different widgets are things that we rank. No? So we want to have the most relevant category shown first, the user. And then inside these categories, we have content items. And these content items are also something that we want to rank. Okay, so now we're interested in off-policy evaluation for these problems. And the data that we observe is implicit feedback that comes in the form of interaction action logs. And for the sake of this talk, I'm going to make the assumption that we have full visibility and that our randomized, that we have a logging policy that's randomized with known propensities. So these logs have the following form. So we have features that characterize the user and the items that we display. Then we have the observed rankings here denoted by capital Y not. Then we have a click indicator that tells us which items actually have been ranked and clicked on. And then we have the logging policy here, and we have in total n different requests. So now our aim is to evaluate the expected number of clicks for a different target policy that we assume deterministic here. And so more formally, this means we have here the expectation over our feature distribution, or over the click model that we use, and then over the policy of the sum of clicks that here C of y. And so importantly, now this is an expectation with respect to a different policy, different from the logging policy. So an approach that we have seen this morning is the use of an IPS estimator. And the form of this is typically the following here. So we sum over requests, we sum over the items that we rank, and we have our clicks. And importantly here, this weight W determines the type of estimator that we use. Okay, sorry, I'm just adjusting this a bit. Okay, so the first model that I'm going to talk about is the position-based model. The position-based model is a click model used for off-policy evaluation. And this model assumes that clicks factor into relevance and examination. And importantly, it is assumed here that relevance is independent of the position, and the examination is independent of the item. And so a clear limitation here that is that, I mean, doing offline evaluation based on the position-based model is only unbiased if the position-based model is correct and if we have access to the true position bias curve. So more formally here, the expectation for a click on an item factors into the relevance of the exposed item and the probability of the item being examined conditional on its rank, right? So here the rank of the item comes into play. And the resulting IPS weight for an estimator based on this approach uses the probability of an item being observed under the target policy divided by the probability of the item being observed under the logging policy. So an advantage of this approach is that we have that this yields a low variance estimate. It's easy to use and it's interpretable. The click model that we use can easily be understood. However, a clear downside is lack of robustness. So as I said, we have to have access to the right position bias curve, and if the click model that we assume is not true, then we will have a biased estimate. Okay, so let me illustrate this a bit using a synthetic example. So here, and this is also the setup for the rest of our experiments, we have synthetically generated data with a full visibility and 10 actions to rank. Our expected reward can be computed analytically in this setting. And here what I do is, so I know I have my true reward that's 2 here. On the right-hand side, you see the correct coverage of the reward for the position-based model that uses the true position bias curve. Whereas here, if I misspecify my position bias curve by taking the true curve to the power of 1.8 component-wise, I'm clearly off, right? And so this is what actually can happen in practice quite easily. Okay, so now another model that's more general is the item position model. I think it was called independent position model this morning. So here the idea is that clicks can both depend on position and relevance. However, items have to be independent of each other, right? So that's also a strong assumption. Okay, so more formally here now, the expectation of a click depends on the item and its rank at the same time. These two don't factor anymore as in the position-based model. Okay, so yeah, joint dependence on item and rank. And the resulting IPS weight here using assuming a deterministic target policy looks at the items where looks at where the rank of the items coincided in logging and target policy and divides it by the probability that the logging policy has put an item in the same position as the target policy, right? So this is where the propensities come into play. So an advantage of this idea is that it is more general, so it makes weaker assumptions than the position-based model. No position bias curve is required. Under the assumptions of this model, it's unbiased with sufficiently randomized data. So you want to make sure that the propensities are bounded away from zero, so that these weights don't blow up too much. And this also is one of the downsides here. We get high variance due to this potentially small propensities. Okay, so let me also illustrate that with some synthetic data here. Again, same setting as before. Now we have our item position model on the right-hand side, so that's the blue curve here. We also recover the true reward, but you see here that we have a substantially increased variance. Okay, so now here comes what we suggest, an estimate that we call interpol. So the idea now is to get the best of both worlds. So we want to move from the high variance, low bias item position model to a low variance, high bias position-based model. And so we do this by introducing a parameter that we call window size here. And so I'm going to give more details on that in a second. And so as we increase the window size, so in window size 0 corresponds to the item position model. As we increase the window size, you see here that the variance goes down. We still recover the true value here. But as we increase the window size, you see now we introduce some bias, right? But the variance stays small, and as we go up and up, we end up at the position-based model now with the wrong position bias curve, with a misspecified position bias curve. But we have introduced some bias, but the variance is smaller of the corresponding estimator. And I think now you get what I want to show here is that there is some kind of mean squared error trade-off between the two, and so we want to find actually suggest an estimate that allows to interpolate between the two. Okay, so let me put this a bit more formally. So as I said, the idea is that we want to reduce the variance of the item position model, and we at the same time we also want to reduce the bias of the position-based model, and we want to find the best approach in a mean squared error sense. And so more formally, we do that by constructing weights here that look at windows where the rank of the logging policy falls inside a close neighborhood of the target policy. And again, we have this kind of we have this indicator here in the numerator. So this quantity is either 0 or 1 for deterministic target policy, and then in the denominator we have the propensities that now don't look at putting an item in a specific position, but putting the item inside a range. And so we have a second factor here, and that's the position bias part. Okay, so importantly, if we set T to the maximum, so this means like to the maximum of items that you're going to rank, we recover the position-based model. So the left factor here is 1 all the time in this case, and the only term that determines the behavior of our estimator is the position bias part. On the other side, if you set this window size here to 0, we recover exactly the item position model, because the position bias part on the right-hand side is basically ruled out by our indicator here that makes sure that that the rank of the target and the rank of the logging have to coincide exactly. Okay, so an advantage of this approach is that we have better empirical performance, as we're going to see. A downside is that we need to choose this hyperparameter T here, that's the window size, and as you see, it's slightly less interpretable. Okay, so let me give you some theoretical results here. So we look at the expectation of this of our estimator, and so what we're able to show is that this estimator is an unbiased estimator of the true reward for all window sizes T, if the logging data is generated from a no logging policy with full support under the position-based model with a known position bias curve. Okay, so why should you care about that? So if you have access to the true position bias. So if your data comes from the position bias model and you have access to the true position bias curve, then our estimator is not going to introduce any bias. So I think that's quite important because you want to make sure that this estimator actually works if your assumptions are correct, right? So, okay. So let me now show you some results. So we did a bias variance decomposition of this estimator, and so what we see here is that for a window size close to 0, the item position model variance dominates, and for the position-based model, so window size equal to 10, here the bias dominates, and we can find an optimal trade-off in terms of the mean squared error that sits around here. So that's a window size of 1 or 2, right? So that gives you like the best estimator in a mean squared error sense. Okay, so let me show you a bit more how this estimator behaves if we vary the position bias misspecification. According to the position bias misspecification, different values of the window size will lead to different mean squared error trade-offs. And so interestingly here, the lower your misspecification, the more you will actually want to use the position-based model, right? So I think this also makes sense. If your position-based model is that you're using is very close to the truth, then you want to regularize a lot to the position-based model. Whereas if your position-based model is like clearly misspecified, you want to take advantage of the item position model. Okay, so this is what we're seeing here. So again, these different misspecification. So the misspecification here is again the position bias curve raised to the power of 0.2 to 2.0. We see if we have access to the true position bias curve, then we have the this dashed line here that gives you the best mean squared error regardless of the window size. No, so this confirms the intuition of the proposition 1. Whereas for different misspecification, you end up at the best window size here would be equal to 1, or something would be equal to here 5 if you're less misspecified. Okay, so let me conclude. So we have shown that we can find an IPS estimator with lower mean squared error when interpolating the item position model and the item position model and the position-based model. So now an open question is, can we show this theoretically? So we want to show that a minimum is actually reached for a window size that's different from 0 or the maximum, right? So we want to actually show that, okay, this minimum exists. So we've also seen that the best window size depends on data set size. So we're showing that in the paper, and the position bias misspecification. An open question now is, can we find the best window size adaptively and in sample, right? So because you don't have access to a mean squared error in practice, so you want to do this using the data that you actually have without knowing the ground truth. We're also interested in a couple of extensions. So an idea here is to apply this to off-policy learning, and then also the handling of the limited visibility, aka a top case setting. So the setting where not all items are observed. Okay, with that, let me thank you for your attention, and you can find more details in the paper.
All right. We have a few questions online. The first one is asking how your method would relate to a sort of doubly robust method. I'm assuming because it's also trying to get the best of sort of both worlds.
Yeah, so I think like a substantial difference with like the doubly robust approach is that we don't have an actual reward regression here. No, so we are operating on the space of click models where we interpolate between two different click models. So the item position model and then the position-based model. So, but it would be also an interesting extension to see how we can use these ideas in the doubly robust approach. Yeah.
Yeah. All right. Then a second question is, why did you restrict the new policy to be deterministic?
Yeah, so that's a good question. So, I mean, first of all, because it was difficult to, so we were starting with some intuition that basically we want to look at ranges where target and locking overlap, because this is where we would have little little bias when doing the estimation. So now the question is, what does this indicator function that I have here look like when you move to something that uses a stochastic target policy? I think that's something that's feasible, but we haven't got to that stage yet.
That sounds fair, yeah.
Yeah.
So then let's thank Alexander again.
Okay, thank you.
And then we have one more speaker before lunch. The speaker is Shashank Gupta, who's a PhD student at the University of Amsterdam, and he did the work VAE-IPS, both with my co-organizer Harrie Oosterhuis and Maarten de Rijke, who's also, I think, a name you will all know.
Thanks, Olivier. And hello, everyone. Thank you for attending the talk. And I couldn't attend it, unfortunately, due to visa issues, but I'm happy to give the talk virtually. So our work is VAE-IPS, a deep generative model for unbiased implicit recommendation. This is joint work with my advisors, Harrie and Maarten. Just quickly, a brief intro about me. I did my master's from IIIT Hyderabad, India in IR. I specifically worked on social media mining. Then I worked at Flipkart, which is an Indian e-commerce company. I was in the search team working on similar problems. Then I started my PhD in IR lab at the University of Amsterdam. And I'm interested in the topics very relevant to the workshop. This is the outline of the talk. I'll start with the motivation of the work. Then I'll we'll define the ideal generative objective for relevance, which is a major focus of the paper. Then learning from log data and from click logs. And then finally, we'll introduce our contribution, which is how to debias a generative click-based objective. Then concluding with some empirical results and challenges. Yes, I'll start with the motivation. So the main motivation for this work is we wanted to model the generative distribution of relevance. So what do I mean by that? For a user item pair UI, where UI is actually generic, U could be query, I could be a document. If it's a search system, and if it's recommendation, then it's user context and item and so on. So we want to model the ideal relevance RUI, which is the actual preference, ideal or actual true preference of the user towards the item I, or more formally, the objective is to learn the probability distribution or probability of true relevance, where theta is a parameter. Now, how do you learn it? So we have the data source which we have access to, usually are user interactions. So the goal is, using user interactions, can we model the likelihood of relevance? Now, some of the challenges with learning from user interaction is user interactions are biased, and we don't get access to R, the true relevance. Instead, we get access to clicks, which are a noisy sort of proxy for relevance. Now, one question is, why generative models? So actually, recommendation is seen as more of a small data problem as opposed to a big data problem. We do have access to a huge log, but for most of the users, I mean, we have very few interactions, right? Most of the users interact with very few items. So this is actually a low data problem. We don't have a lot of data to infer their true relevance. And it is known that we know that discriminative models can overfit in low data setting, whereas a Bayesian or generative model, by design, because of modeling of uncertainty, work well in this low data setting. So hence they are more suitable for user modeling tasks. This is why we are interested in defining a generative model for relevance or for user modeling tasks. Now comes the first part. So how does a ideal, or how does a generative distribution or generative objective for relevance look like? So to get a more intuition, so the generative story for relevance, so we assume relevance as a random variable. So its generative story is, so for each user, we have the user's latent factor, which could encode the user's preference and other features, right? Similarly, for item, we have the latent factor of the item, which we typically don't have access to, and we estimate them using matrix factorization and so on. Now, once you draw the latent vector for user and item, so here we assume that the relevance is binary, that is 0 and 1, but it can be extended to other setting also. But we work with the binary setting. So the just to get the user's affinity towards the item, you just simply take the dot product. This dot product will give the affinity of user towards the item. Now we just, passing it through sigmoid just gives a probability value. So the raw affinity score can be now interpreted as a probability. Now you just simply draw from a Bernoulli distribution from that probability. This is how we get the ideal relevance of the user towards item I. Now this is the generative story. Now, how do you define it mathematically? The loss function. So this is the standard VAE objective. So in VAE, the first part is conditional likelihood, and the second part is your KL divergence regularizer. So in our case, the conditional likelihood, it's simple. So it's just the conditional likelihood of relevance given the latent vector of user and item. So if you, intuitively, if you remove this expectation part, this is very similar to a matrix factorization model, right? So if you assume a Gaussian distribution, then this reduces to squared loss. And if you assume a Bernoulli distribution, then it's familiar cross entropy loss. Similarly, if we, so since we, as I said, we assume a binary relevance, so this reduces to the familiar cross entropy loss with this additional expectation over the latent variables. So since we're introducing latent variables, we're just taking expectation over it. Otherwise, it's the familiar standard cross entropy loss for relevance with additional KL regularizer between the your latent variables posterior and a prior. This is just a regularizer term. So this is the ideal objective. We define this as the ideal objective for relevance. But as we all know, we don't have access to this R. So what we have access to are clicks. So how do you learn from click logs? So similar to this, we define the click-based objective, which is just simply replacing the relevance with what we have, which is clicks. This is again conditional click likelihood, and this is again similar a regularizer term. But this is a biased estimate of our ideal objective. And if we just plain optimize for this, this can lead to a biased recommender system, right? Which will recommend popular items more often than other items because of the skew in the click distribution, right? So now the question is, you have access to click logs and you have a model, but this is not what we want to optimize. So this is bias. So now the question is, can we correct for bias? So this is where we introduce our method. So to correct for bias, we use the standard trick. So this is nothing very fancy. We use inverse propensity scoring. Now we assume a click model. So we assume a simple position-based click model where the probability of click is simply the product of the probability of exposure and the probability of relevance. So you can see this O is the confounding factor between click and relevance. And we define the propensity score as the probability of exposure. So in a popularity bias setting, some items will have more likelihood of getting exposed, whereas some items will have less likelihood of getting exposed. So this propensity score will vary depending on the item's popularity, which is based on the current logging policy. Okay, so now we have the propensity score and we have the click-based objective. So we define our IPS objective, IPS generative objective, as simply IPS weighted likelihood. So this part is different from the click part. This part is, since it's a regularizer, it stays the same. So we weigh the click likelihood with propensities. So what more specifically, we scale the labels with the propensity. Right, this is this we take expectation over the latent variable. Now this is, it's easy to see that this is an unbiased estimate of our ideal relevance objective. It's easy to see, but if you want to look at the proof, you can go through our paper. So now we have defined the IPS based generative objective. Now, does it work actually? So now let's look at some experiments. We have two experimental setup. One is a semi-synthetic setup where we use the movie lens data set. But the problem with movie lens data set is the whole data set is, we don't know what policy was used to generate the data set. And to evaluate an unbiased method, you need access to an unbiased test set, which is free from any kind of bias, right? Otherwise, your evaluation will also be biased. So we create a semi-synthetic test set where we resample. So we split the data into training and test, and we resample the test data with this probability, which is again, inverse probability. So if you do that, we get almost uniform popularity distribution in test set. It's almost uniform because there's still sampling bias because of the resampling. So you don't get exactly a uniform popularity distribution in the test set. But our goal is sort of achieved. So we basically want a different distribution in test set than in the train set. We also have access to Yahoo R3 dataset, which has an ideal test set, which was collected under a uniformly random policy. So that's an ideal setup. And lastly, for variance reduction, we use propensity clipping. So we clip propensity to a minimum value because there's an inverse term, because propensity is 1 by probability, and if probabilities are too low, you can get very high variance. Now, some experimental results on semi-synthetic data. Now we have only shown the results with just one setting, where the test resampling probability is 1 by square root over probability. If you are interested in more, we have more details also in the paper. So the methods we compare against are matrix factorization with inverse propensity scoring, where we optimize a cross entropy loss with IPS weighing. And this is the IPS corrected matrix factorization. We also have a doubly robust matrix factorization, and also a recent baseline called dual unbiased matrix factorization, where they slightly modify the negative part of the IPS negative part of the loss function. So in the cross entropy, we have a negative part. So they modify it slightly different than the plain IPS correction for matrix factorization. Now, from the result, and we evaluate on ranking matrix, map at K and NDCG at K. So as you can see, the IPS corrected VAE performs best amongst all. One interesting thing in semi-synthetic setting is VAE without any correction, it performs better than other linear models with IPS correction. So we hypothesize that this is because of, so these all the methods, they assume the propensity scores to be known, but we don't have access to propensity. We estimate it from the data. So there's a specification error, right? There's an error in propensity computation, and also there's an sampling error. So so both of these effects combined, a plain linear model plus IPS correction, they don't perform very well in semi-synthetic setting. And with Yahoo, the data sets are more in line to expectation, where the matrix factorization with IPS correction, it performs better than other baselines, and our method IPS with a VAE that performs better. So these are the results. And now to conclude my talk, some of the challenges which I think are not currently addressed are so propensity estimation. So most of the methods currently, they use simple count-based propensity. So they just count the number of times an item was clicked. And the idea is if the item was clicked many times, so it should be given low weight. But if the item was clicked less times, it should be given higher weight. But we know that count methods have problems, right? Specifically in low data setting. If you just have, let's say, if an item was impressed 5 times and it got clicked 2 times, it has high CTR, but I mean, that estimate is not very reliable, right? So one question is, can we come up with more sophisticated propensity estimation methods? Also, can we model more complex UI, like recommendation, not just top one item, right? We have Spotify, YouTube, where we have grid light setting, where neighboring items can affect the click probability and so on. And also, can we incorporate more complex click model, like Yuta talked about in his talk, in this framework? And finally, to conclude, we defined an ideal generative objective for modeling relevance. Then it's click-based version when learning from click data. Then we propose an IPS-based correction. And finally, we had some empirical results. Lastly, thank you for listening. If you have any questions, please feel free to email me here or just ping me on Twitter. And you can also find my other works on my website. And this is the QR code for questions. Thank you. I'll be happy to take questions. I hope I was audible throughout the talk.
All right. Yes, you were very loud and clear in the room, Shashank. So
Okay.
Thank you for that. We have a few questions online already. First one is, would this be something that you can extend to the multi-VAE setting, where you have a multinomial likelihood instead?
Yes. So as I said, I mean, we assume a binary relevance, but it can be extended to a multinomial distribution or other setting. So the VAE part is, I mean, generic. You can use multi-VAE. We used there's something called bi-VAE, but I mean, you can replace it with VAE of your choice.
Okay, that sounds great. Then a second question, do you have any results showing how the method's performance would degrade when you have wrongly specified propensities?
Like in this paper, we didn't include it, but I'm working on it. So, I mean, I don't have the results yet.
Okay.
That
okay.
I can, yeah.
That's absolutely fine. I think it's very nice to see this work in progress. And then the last question is whether this method is extendable to doubly robust estimation.
Yes. So I think if you look at this part, this is if you ignore the expectation part, this is similar to matrix factorization, IPS. So we can add a regression model and turn it into a doubly robust. So yes, this can be extended.
Okay, that all sounds really great. Then let's thank Shashank again.
Thank you very much.
Right. Then I would just like to thank all of you who are still here, probably very hungry for lunch now. So we will let you go and do just that. We will be back at 2:15 with our second keynote of the day. It will be given by no one less than Guido Imbens. So we are really, really looking forward to that. and I hope you will all be as well. So I'll see you then.
I hope you all had a good lunch and are ready from our next keynote, which is quite the speaker. We have Guido Imbens. Guido Imbens is the Applied Econometrics Professor and Professor of Economics at Stanford Graduate School of Business. He graduated from Brown University and taught at Harvard University, UCLA, and UC Berkeley. He specialized in econometrics and in particular methods for drawing causal inferences. He's a fellow of the Econometric Society and American Academy of Arts and Sciences. But most famously, in 2021, he was co-awarded the Sveriges Riksbank Prize in Economic Sciences in memory of Alfred Nobel for their methodological contributions to the analysis of causal relationships. Let's welcome our speaker, Guido Imbens.
All right, thanks very much, Harrie, for that introduction. Thanks, Harrie and Olivier, for organizing this together and being here. It's a great pleasure to be here. Again, thanks, Harrie, for that introduction. When I got that call from Stockholm last year, that was a very interesting experience. One of the interesting things was that NPR later that day said that Josh Engers and I shared the prize for our analysis of casual relationships, which greatly confused our spouses. So what I want to talk about today here is a project I've been working on for a while with some collaborators, many of them actually local here at Amazon, including Pat Byrie, James McQueen, and Lorenzo Macero, and Thomas Richardson, who's at Washington University, also here. And so, kind of starting point was that we're thinking about experimentation in some of the settings where the tech companies do experiments. And so, to kind of make it specific, suppose we're thinking about offering customers kind of in an online marketplace. Suppose we're thinking about offering customers more information about products, and then we want to see what the effect is of such a change on how much they engage with those products, how much they purchase, and kind of before making a decision on whether to implement that the change, we want to predict what the effect is going to be. And so a simple way of doing that might be to do an experiment. And there's really two ways of doing a conventional A/B test, a conventional randomized experiment, going back kind of to the work by Fisher and Neyman in the 1920s and 30s. The one thing we could do is do a product experiment where we say, well, we have a set of products kind of here in this example, there's 8 products, but it could be a very large number of them. We could randomize them into 2 groups, one control group, one treatment group, where the control group, the control set of products, doesn't get the additional information, and the treatment group, the products in the treatment group, we show the additional information about those products to all the customers. So that would be one way of doing an experiment. We could also do a customer experiment. We could randomize the customers into 2 groups. Here, there's just 5 customers, but it could be a lot of them. And we could provide the additional information for all the products to the customers in the treatment group and not to the customers in the control group. And kind of traditionally, the way to do experimentation there would be to make a choice between those 2 types of experiments. And kind of once you make the choice, kind of the way you would do the assignment, you would measure the outcomes, and you would estimate the average effect of the change of giving the additional information by comparing the average outcomes for the treated units, whether that's the treated products or the treated customers, and the control units. And you would estimate the variance of that, and you kind of would be done. And we'd essentially be using the methodology going back to Fisher and Neyman, and that would all be well established and well understood. But it doesn't really work very well in many of the settings where the experimentation is done online these days. In many cases, the problem is that the units are not separate, are not distinct, but actually interact in complex, in intentional ways, leading to interference between units, leading to spillovers between units. Treating one particular customer may have an effect on the outcome for other customers, and similarly, treating one particular product may have an effect on outcomes for another product. So think, for example, in the case of a rideshare company, Uber and Lyft, if I change the incentives for one particular rider to get a ride or not, that's going to affect other customers. If that first customer who gets treated decides to get a ride that he otherwise would not have gotten, that has an effect on other potential riders, because the particular driver who is taking that rider somewhere is no longer available at that point in time. That's going to be a very small effect if there's just one customer treated, but if you treat a very large number of customers, the fact that that changes the market, that it changes how many drivers are available, can have a substantial effect on the riders in the control group. Similarly, for the rental agency, for Airbnb, if you change the experience for some rentals, that may make those rentals more or less attractive, and that may, because of that, have an effect on the rentals in the control group, if customers are more likely to now choose the units in the treatment group. And standard A/B tests ignore these problems, and they don't. And moreover, they don't allow us to even see that there's a problem with these spillovers. All we can do there is compare two groups, and we get an estimate of the difference, but that's combining both the direct effects and the indirect effects coming from these spillovers. And in many of these marketplaces, these spillovers or interactions are intrinsic, and they're really not something we can avoid in a very simple way. So what the main general ideas in this paper is to think of these cases of the assignment not as a factor where we have a population of units that are partitioned into two groups, but to think of it in this case as a setting where we have two populations and where the assignment as a result is a matrix rather than a factor, where we can assign the treatment, say the additional information, to separately to every pair of products and customers. And we don't necessarily need to have a particular customer have the same experience for all products, or have a particular product have the same experience for all customers. And so the key requirement here is going to be that both the assignment can be determined at the level of the pair here, customer and product, and the outcome can be measured at the level of the pair, customer, product. So the outcome can be something like engagement or how much the customer spend on a particular product, but it's something that can be measured at the level of the pair, customer, product. And so in this setup, the standard A/B tests are just a special case. A customer experiment would be a special case of these multiple randomization designs, where we insist that the rows of these of the assignment matrix, or where the columns of the assignment matrix are all the same, or where the rows are constant, and a product experiment would be the special case where every row in the assignment matrix is identical. But of course, we don't have to restrict ourselves to these special cases. In principle, we can choose any particular configuration of assignments. And by doing that, we can learn more interesting things. We can do more interesting things than we would get out of just a customer or product experiment. And so a very simple case of the type of experimental design we're proposing in this paper is what we call a simple multiple randomization design, where we select randomly a set of customers. Here, customers 3, 4, and 5. We randomly select a set of products. Here, products 5, 6, 7, and 8. And the customer pairs, where both the product and the customer is selected, are assigned to the treatment group, and all other product customer pairs are assigned to the control group, are exposed to the control treatment. And what the sort of key insight is that by doing the assignment in this way, we generate 3 distinct control groups that ex ante are comparable because of the randomization. The red Cs, the blue Cs, and the green Cs ex ante are comparable. There's nothing that makes them different, and they're all in the control group, but exposed, they have systematically different experiences. The green Cs in particular are customers where, even though they're assigned to the control group for that particular product, they sometimes experience the active treatment, the new treatment. And so if there's spillovers between products for the same customer, if the treatment makes some products more attractive than others and makes customers switch from control products to treatment products, you would see that in comparing outcomes for the green Cs and the red Cs. And so what we're going to get out of this type of experimentation is, first of all, the ability to actually learn to detect spillovers between units, where a standard customer or standard product experiment would not allow us to do so. And so what we're going to look at kind of more generally, and we're going to look at more complex designs there. We're going to look at setting where we have 2 or more populations with the outcomes indexed by both, and that can be, and that's the example I'm going to use most of the time, customers or products. In rideshare companies, there could be drivers and riders. In other cases, there could be products and time periods, days or weeks. And we can choose to randomize the units from one of the 2 populations and use conventional A/B experiments. But more interestingly, we can assign the treatment to the pair customer product in deliberate ways to learn more. And that's going to have 3 benefits. One is that even if there's no concern about spillovers, these designs can be more efficient, can be more powerful in estimating the effect of interventions. And so we can do better than standard experiments. But the most important benefits are the last 2, that if there are spillovers, these designs can help us detect the presence of these spillovers. And they can allow us, under some assumptions, and this is not going to be assumption-free in general, despite the randomization, despite the experimentation, but they can help us adjust for some of these spillovers and still estimate what the effect would be if all units, if all pairs of customers' products would be assigned to the new treatment versus nobody would be assigned to the new treatment. We're going to have to limit the spillovers there. We can't have completely unrestricted spillovers, but if we're willing to put structure on there along the lines of these spillovers are determined by how many of the products are treated for a particular customer, or how many customers are treated for a particular product, they can help us extrapolate to what would happen if nobody was exposed to the treatment, or if everybody was exposed to the treatment. And so what I want to do in the rest of the talk is kind of go through that a little bit more detail, how such experiments would work and what we could learn from them, and also kind of look at richer versions of these. But kind of for the generic example, I'm going to look at a case where the 2 populations are customers and products. And we're thinking about a binary treatment, say, providing more information about a particular product to a customer, where we can do that, where we can apply that treatment at the level of the customer product pair. Of course, that's something where the fact that much of the experimentation these days is through electronic means, is online, makes it very different from traditional experiments. If we did this in a grocery store, you couldn't really give different customers a different experience at the same point in time. But online, we can provide different information to different customers. And sort of the question we may be interested in is what would happen if we exposed all customers' products to the treatment relative to what would happen if we exposed none of the customer product combinations to the new treatment. And the key requirement is going to be that we can choose the treatment at the level of the customer product pair. And even so, the traditional settings, that's often not possible. And even here, it may not always be applicable, and it may create other concerns. But here, we're going to look at settings where that's possible, and we can measure the outcome at the level of the customer product pair. And so, as an example of kind of more complex designs beyond that simple multiple randomization design, here's an example of a design that could help detect effects of strategic response on the part of the sellers, where they may respond to customers being exposed to the treatment. And so here, the design consists of two stages, where in the first stage, the products are randomly assigned to one of two groups, the A or B. The products in category A, for the products in category A, we then do a customer experiment for all the customers. And for the products in group B, we do a product experiment for all the customers. And so that generates here, kind of again indicated by these three color-coded C's, that generates three different sets of control pairs of customers' products that are ex ante comparable, but are exposed, have similar systematic experiences in general, despite all being in the control group. And similarly for the treated subpopulation, there's three subpopulations that are different exposed in their overall experience. And so comparisons of these three control groups and comparisons of these three treatment groups are going to allow us to estimate the spillovers of various types and allow us, under some assumptions, to extrapolate to what would happen if everybody was exposed to the treatment versus nobody was exposed to the treatment. And so the questions we're kind of interested in general in this paper. So what are the objects of interest? And so I'm mainly going to focus on just the overall average effect. Second question is, how should we actually design the experiment? Once we have the ability to assign the treatment at the customer product level, the question of what a good distribution for that assignment matrix is a much more complex one. In standard experiments, the optimal thing is almost always something very close to just assigning 50% of the units to the treatment group and 50% of the units to the control group. Here, the optimal assignment is much more complex because it's going to depend on how much spillovers there are and what we know about the nature and the magnitude of these spillovers. If we know, in some cases, it's still a very easy question to answer. If we know that there's no spillovers whatsoever, then the optimal thing would be to randomize both within customers and within products in a way that all the customers are balanced and all the products are balanced. But once there are spillovers, the optimal design is going to depend intricately on the magnitude of these and the nature of these spillovers. And then the statistical question is how we estimate the objects of interest and how we do inference. And there, the inference methods we developed are very much in line with the name and style inference that is based on the randomization rather than model-based, though we do require some modeling assumptions about the nature of the spillovers. So to set up a little bit more notation, I'm going to look at a case where we have the capital I customers indexed by I is 1 to the capital I, and capital J products, J running from 1 to capital J. Outcomes are indexed, Y indexed by I and J, and the treatment is binary, is W also indexed by I and J. And so for some of the inference results, and I'm not going to go into detail in this talk anyway, but for some of the inference results, we are going to rely on both I and J being relatively large. There's going to be some approximations there, though many of the results can actually be the exact finite sample, the results relying on the randomization distribution. So as I said before, if we think about the design question, we're going to think about what is a good choice for the distribution of W. Here, that the optimal, the answers to that question are going to depend on what assumptions we're willing to make about potential spillovers and correlation of outcomes. One critical assumption would be to assume that the spillovers only happen within the rows and the columns of that matrix, that treatment assignment for the unit I, for customer I and product J, only affects outcomes for the same customer, but possibly for other products, or for other products, but the same customer. That's still a very restrictive assumption, and there's many settings where you would expect the spillovers to go much further, but that's kind of a natural extension of the case with no spillovers whatsoever, or spillovers that are restricted either within customers or within rows. But I think that's really important to stress here, is that once you generalize from no spillovers, you're always going to need to make assumptions about the nature and the form of the spillovers to make some progress. So let me first look at a very simple case of these multiple randomization designs that is particularly attractive if there's no spillovers whatsoever. So in that case, the optimal thing to do would be to randomize the assignment to the treatment both within the customers and within the product, so that every customer is exposed to equal number of for an equal number of products to the new treatment and to the controlled treatment, and every product is exposed to the new treatment for an equal number of customers. And so that's going to be much more efficient than doing a pure customer experiment or doing a pure product experiment, even though both of those would still be fine and lead to unbiased estimates of the average effect. But balancing things both within customers and products is going to improve the efficiency. And so you kind of, to just show that in a very simple setting, if the outcomes are additive in the customer specific component, the product specific component, and an idiosyncratic one, you can see that the variance of the difference in means between treated and controls for a completely randomized experiment is going to be of the order 1 over I times J. So it's proportional to 1 over the product of the number of customers and products. And for a customer experiment, it will only be proportional to 1 over the number of customers. And so you would have a much more efficient experiment if you randomize both within customers and products. So another version of that actually goes back to the much earlier experimental literature is the crossover experiment, where one of the dimensions is time. And so this is the type of experiment that we do in agricultural settings with feed for cows, where they would switch from one day to the next, as well as between cows. And again, that was done largely for efficiency reasons. And it's a type of experiment that is still done in some of the rideshare companies, where they switch treatments over time to get to avoid having to deal with the spillovers within markets at a particular point in time. Now, the more interesting case is the simple double randomization design, where we're interested in actually learning about spillovers. And so there we first randomize one of the populations, say the customers, into a number of groups. Then we randomize products into a number of groups, and we assign the pairs, the customer product pairs, to the treatment as a function of the assignments to the customer and to the products. So the simplest case, where we have two groups for the products and two groups for the customers, this is the type of design you could get, where a selected set of customers is exposed to the treatment for a selected set of products. That gives us these three control groups that are ex ante comparable, but are exposed to have different experiences. And so in particular, the RecSys here are what we call consistent controls. These are customers that are always exposed to the control treatment, and products that are always exposed to the control treatment. The green Cs are what we call inconsistent customer controls. There, the customers are sometimes for other products exposed to the treatment, but for these particular products, they're exposed to the control treatment. And so if the spillovers are of the nature that customers may be inclined to substitute between control and treated products, comparing the inconsistent customer controls and the consistent controls would allow us to learn about that type of spillovers. For the blue Cs, what we call the inconsistent product controls, the products are sometimes exposed to the treatment for other customers, but not for these customers. And so if there's a setting where sellers, as a result of some customers being exposed to the treatment, are incentivized to change the experience by providing additional information or giving discounts, but they have to do so in a way that is the same for everybody, then these blue controls will be different from the red controls. And by comparing the outcomes for the blue controls and the red controls, we can learn about the effect of spillovers coming from the seller side of the market. And so in principle, there's a whole bunch of comparisons we can do here. We can simply compare all the treated units to all the controls, but that's going to involve a number of potential biases relative to the overall average effect. If we're interested in estimating the effect of the treatment, if we expose everybody to the treatment versus nobody, the most direct comparison is comparing the outcomes for the treated and those for the consistent controls. And if we're interested in learning about spillovers within the products, we can compare the blue Cs and the red Cs. And if we're interested in comparing spillovers within customers, we can compare the green Cs and the red Cs. And if you actually want to take those out of all the comparisons, we can do this double difference that under some conditions is going to give us the most credible estimate of what the effect would be of exposing everybody to the treatment versus nobody to the treatment. Now, let me look at another setting where these multiple randomization designs can also be helpful. And that's in problems where clustering is used to deal with spillovers. So in many settings, we're concerned that simply randomizing, say, at a product level isn't going to give us the right answer, isn't going to tell us what would happen if we exposed all the units to the treatment versus none of the units to the treatment. And the reason is often that we would expect customers to switch between control and substitute between control and treated products. And so what people often do in those cases is group products together in clusters of similar products so that most of the spillovers are present within these clusters, but not across clusters. And then just do a simple experiment with the cluster of products as the unit rather than the original products. And such an experiment may be very effective if the question is solely about the overall average effect, but it doesn't actually tell us much about what the magnitude of these spillovers is. And learning about the magnitude of these spillovers can be important, partly because it may tell us whether we actually need to do this type of cluster experiment in the future, or whether it would be more efficient and cheaper to do the experiments at the product level. And so one approach to learning both about the overall effect as well as about the spillovers is to combine the cluster randomized experiments with multiple randomization. And so what we could do is split the customers into two groups, denoted here by A and B, where the customers in the first group, kind of the A group, are then part of a clustered experiment where the assignment to the treatment for the products is constant within clusters. And so the first cluster, all the customers in this group A are in the control group. For the second cluster, all customers are in the treatment group. And the assignment is constant within this cluster for these customers. And the second set of customers, here denoted by B, is part of a product experiment where we assign the treatment at the level of the product, and we randomize completely irrespective of the cluster. And so again, that gives us a number of different product customer pairs that ex ante are the same because of the randomization, but now exposed allow us to assess what the effect is of the spillovers within the clusters. So in particular, if we compare the brown Cs which are customers in group B that are exposed to the control treatment, but not in a consistent way, and we compare them to the blue Cs, we can learn about what the effect are of the spillovers within clusters. If the concern is that customers are going to substitute within the clusters, we would see that some of the demand for these products would move from product 2 to product 1, say if the treated products are more attractive, and we would see a systematic difference between the control outcomes for product 2 for customers in group A versus customers in group B. And so again, unlike a clustered experiment that would allow you to directly estimate the overall average effect, but not allow you to learn about the magnitude of the spillovers, here within the same experiment, validated by the randomization, we can learn both about the effects we're interested in, as well as the amount of the spillovers by comparing these groups. So let me then wrap up, because I want to make sure that there's going to be time for questions here. What we're trying to do in this paper, and the paper kind of has much more detail on how to do inference in these settings, but we're interested in developing the methods for experimental designs that allow us to learn about and adjust for spillovers of the type that arise in online marketplaces, where spillovers between units, where strategic interactions between units are intrinsic to the way these marketplaces are set up. And the specific way in which these interactions and spillovers take place often depends on the particular setting, kind of, and the structure of these interactions. For example, in the rideshare companies, it's not that the riders directly interact with each other. Their interactions are mediated by the platform, and so they're anonymous. They're through the effect they have on demand for the riders, and that helps us put structure on the spillovers you would see in the data, and that helps design experiments that can actually address that type of spillovers. And that's going to be different in other settings where individuals or other units interact more directly, and possibly only within subsets of the units. In many of the cases, the interactions are limited to particular subsets, say substitutes in product spaces, or sort of locations in the case of rental units in settings like Airbnb. But in all cases, the particular platform puts limits, puts structure on these interactions that can help us design experiments that answer both the questions about the overall effect of changes to the structure of the market, as well as about questions about the magnitude of the spillovers. And so that creates a lot of new questions about how to design these experiments. It creates a lot of new questions about how to do inference. That's going to be more challenging than in the standard experiments. And it creates an important role for modeling, and often that's going to involve economic modeling on how the two sides of these markets behave and how they interact with each other in a way that creates these and limits these spillovers. So let me then open it up for questions here.
Thank you very much. Thank you very much, Guido. We have, just to inform you, we have about 60 people online watching as well. So we're going to try and separate the questions between the online and the offline audience. But let's start with the offline audience. Yes.
Thank you for the great talk. This is Ian from Google Brain. I actually have a question on the spillover effects. I wonder, have you considered a case if the spillover effect would happen on both dimensions at the same time?
Yes. So what we've done in the paper is kind of focus on the case where the spillovers can happen both within products and within the customers. So kind of specifically, we say that changing the treatment exposure for customer I and product J can affect the outcome for customer I and other products, and it can affect the outcome for product J and other customers, but it cannot affect the outcome for a different customer and a different product at the same time.
Yeah.
So that's still not quite good enough, because you would expect that in many cases these effects kind of do cascade. So if treating customer I and product J affects another customer for that same product, then it's likely that it would also affect another product for that other customer. And so then it would be cascading down to the kind of, it could in principle affect everybody. And so you would need to put additional structure on these effects decaying at some rate. And so in the case we analyzed, kind of we focused on setting where we could get kind of very clean results. And so we didn't consider that case, but so it would be important to go further where you allow for these effects to go beyond just within the rows and just within the columns. But we already allow for both those effects within the same experiment.
I see. Yeah, thanks.
Hi, thank you for the talk. So when you cluster the group to choose who will be treated, you're choosing the group to be treated, right? So how do you? I'm just not following the difference between the. You're not randomizing it, so how do you distinguish the group effect, and the actual effect of the treatment?
Well, so here we first randomly assign these customers to two groups. So customers 1 through 4 are ex ante completely comparable to customers 5, 6, 7, and 8. So at that point, there's no difference. They would be, at least in expectation, balanced in all their characteristics and propensity to engage with these products. Then for the first set of customers, we do this clustered experiment. So suppose that kind of these clusters are just pairs of product that are really very similar. And so if the treatment is we give you a discount on one of these things, then everybody who would be inclined to buy one of these things would buy the one with the discount. And so you would see for customers in group B that if the treatment is this discount, nobody would buy product 2 because they would all buy product 1 because it's essentially the same product just with a discount. And so you would see that the outcome of its purchases for the product 2 in group B would essentially be 0. But in group A, people would still be indifferent between product 1 and product 2 because they both got that discount. So now what the key thing is you see a difference, systematic difference for product 2 between these people who were in the clustered experiment and the people who were in the product experiment. And that coming from the fact that a substitution between products in the same cluster. And so if you didn't need the clusters, if there was no substitution at all, then you would find no systematic difference between outcomes for the group A and group B for product 2 and products like those.
Right, we have a question with the highest number of votes on the website. It's an anonymous question. I'll ask it for this person, of course. The question goes, intuitively, it seems like we might lose statistical power by dividing the data in 4 groups. I think AA, AB, BA, BB, etc. instead of 2, AB. Could we somehow leverage observational data to help here?
So first part of that is yes, by grouping these systematically into 4 groups, even if these are ex ante are comparable, we're going to lose power relative to just grouping them into 2 groups. Kind of, another way of saying that we're trying to ask more questions of the data of the same number of units, and so we're going to lose something there. Now, then the second part of the question, that's kind of a very interesting question. So can we leverage observational data in order to improve things there? I think that's true in general if we're doing experiments, and I think we're not doing enough of that. We typically have huge amounts of observational data that are both much more representative and have much more detail and are much bigger than the experimental data we're going to have. And so finding ways of systematically combining them in order to get more precise and more credible answers out of the experiments is going to be very useful strategy. So I've done some work on that kind of in a slightly different setting where we were looking at combining experimental data where the experiments are relatively short term and we're interested in long-term outcomes. Obviously, in many cases, we're not really interested in kind of just the short-term outcomes we measure in these experiments. We want to know what these things do in terms of long-term engagement of various types. But we can't do these experiments over very long periods of time. So we need to combine the experimental data with observational data to get a handle on those questions. For this specific case, I've not thought in detail about how to bring in the observational data, but the same type of issues are going to come into play. And I think it's going to be very valuable to do that in a systematic way. And kind of beyond that, we already see that we need to make assumptions about the nature of the spillovers. We need to make assumptions about the behavior of these individuals. And so even though we do experimentation, you kind of need to be wary of the notion that just because you're doing experimentation, you don't need to make strong assumptions on the behavior of these individuals. That works well in these very special cases where nobody affects what happens to anybody else, and that's very plausible in some cases. If we do experiments on plots of land, I mean, we put horse manure here and cow manure there, these plots of land don't interact, they don't talk to each other. And it may work in medical settings if it's particular treatments where the patients don't interact. But in many cases, and in all the, in lots of social science settings, we know that these spillovers and interactions are hugely important. And experimentation doesn't give us a clean way of completely getting out of that. We do need to make assumptions about these things. Because if everybody interacts with everybody else, we don't have replication in a way that we can learn about these effects and estimate and do inference for these things. So the fact that if you're bringing in observational data, we would need to make modeling assumptions about how to do that exactly, shouldn't make us shy away from doing those things, because we're already forced to do so by putting structure on the spillovers.
Thank you very much for the clear answer. In a similar vein, another question from the online audience. In your opinion, why haven't we seen more adoption of within subject, so repeated measures, blocks designs? So within subject, sorry, let me just start over. Why haven't we seen more adoption of within subject designs that allow us to expose the same subject to both T and C over the course of an experiment?
So I think in many cases that would be very useful to do, but the concern obviously is that that people may see what the treatment they're exposed to, and their response may take a while to settle in response to the new treatment. So if say Airbnb changed their website completely and then switched it again the next day and the day after, that would be very confusing for people, and that would not tell you what would happen if they changed the interface permanently. And so when you do that type of experiments, you need to be very cognizant of the fact that it takes some time for the new equilibrium to settle in. And again, that's very different from some experiments in other settings where these changes would be instantaneously. But here, if the subjects are individuals who are behaving strategically and who have memory of their previous experiences, that's going to be an important thing.
So in your opinion, are there cases, should there be more adoption of this? Are there cases where this can be done, but they don't?
So I mean, I think in general, we need to do a lot more. We do need to do a lot more complex, a lot more richer type of experiments. We need to experiment more with what type of experimentation is actually effective. I think for a long time, the experimentation has really focused very narrowly on traditional types of experimentation, traditional types of A/B tests of the type. Again, they go back to the 1920s, but the settings you guys all are looking at nowadays are much richer and much more interesting, and that's kind of led to this whole literature on doing experimentation in a much more interesting way. And so I think we need to learn much more about what things work well there.
Absolutely. Thanks. We're going to go for another question from the audience here.
Thank you, Professor. Very inspiring talk. I have a question like, obviously here your method applied to two random variables. One is the user, another one is item. Can this method can be easily extended to the more number of random variables? This is the first question. Sorry, another one. When you assign the treatment group, I noticed you have a different way to assign that Wij for the treatment. Is there any underlying guideline to say what is the guideline if I want to design that? What is the guideline behind to determine that matrix? Thank you.
Yeah. So first part, yes, we focus mainly on the case where there's two populations, but in many cases you can but conceptually, there's no reason to limit it to 2 cases. There could be 3 or 4. In many cases, you can change things over time, as well as products and customers. And clearly, that would give you an even richer set of possible designs, and keeping the same way what I said at the beginning. Sort of once you realize that the assignment can be a matrix rather than a vector, restricting all the columns to be the same doesn't make sense. And now if you can do this in 3 dimensions, keeping one of the dimensions fixed is in general suboptimal. So it would make a lot of sense of varying the exposure over time, as well as between the products and customers, to learn about the additional changes. And so second part of the question, actually, I don't remember exactly what this was about, how to actually implement these, how to do the randomization over time.
The second question is for each of your treatments, what they call the method. There is a treatment group assignment. So their matrix, I remember it's W, IJ.
Yeah.
Like, so either it's treatment, T or C, right? So what is the underlying guideline to construct that matrix? Basically, how?
But
yeah.
so that goes back to the question, kind of, how do we actually choose the matrix? How do we choose the distribution in a particular case? And all we've done kind of so far for some of the cases I was involved in is kind of do simulations to figure out what are effective designs. It becomes a much harder question than it does in the case where there's only one population. I kind of mentioned briefly that in the simple case, kind of the optimal thing, or at least close to optimal thing, is just almost always put 50% in the treatment group and 50% in the control group. But in the case, even if it's just a matrix, forget about the case where it's a 3 or 4 dimensional object. Even in the case of a matrix, it's not clear what the optimal thing is, because it depends immediately on what the nature of the spillovers is. If there's no spillovers, then it's still a simple question. You should balance things both in the rows and the columns. But if there's spillovers, it's going to depend on how you're actually going to estimate the average effect, how you adjust for the spillovers that are still remaining, and then how big these spillovers are, what the optimal design would be. So it's not easy. We've not been particularly successful in kind of formulating that as in a way that is clear answers. It's kind of what we've done is just some simulations to suggest that particular things work well, but that's still very unsatisfactory. And so the power type calculations and the design questions are still much more complex than what we've been able to answer.
Thanks for the answer. Right now, in the back here, in case you lost
Yeah.
us, we have a question from the audience.
Thank you. My name is Kim from Shopify. So if you want to test a visual change on your website, for example, and if I go and see that visual change on one product and I don't see it on the next one, then in the end, it would be a much more frustrating experience for me, because I would see there is something wrong on the website rather than the experience would be better one place than the other place. That's the first question I have. The second question is, if we cluster one type of products into the treatment or into the control, isn't that then a confounding factor also? Since that if I do a visual change that fits better with children books, for example, and I only show the treatment for children books, do I then know if it's the change that I'm seeing that works better, or is it just because it's children book?
Yes, I think those are all important concerns, and that's sort of what makes it so hard to figure out what is an effective way of doing the experimentation for that type of questions. It may well be that in some cases, if we do an experiment where as soon as where a customer has an inconsistent experience, but sometimes even if only once they're exposed to the new treatment and the rest of the time in the control group, they're already affected by that one exposure to the treatment group that may change their whole mindset, that may leave them frustrated. And so figuring out and understanding what the potential nature is of these spillovers is going to be very important in figuring out what are effective ways of doing the experimentation. And so in some cases, those concerns might be so big that you really need to insist on customers having a consistent experience the entire time. But that puts a lot of limitations on what you can actually learn from the data.
Could this be a situation where if you find out about those spillovers that you throw away part of your data, let's say, because you no longer use it because of that?
Yeah, well, and but if you're going to throw away some of the data, then you probably shouldn't design the experiment in that way to begin with. And sort of, but it's going to be hard figuring out the answer to these questions through experiments in these cases where these spillovers are very substantial.
I see. We have more. Yes. Yeah.
Hi, Guido. Very nice to see you again, and very nice talk. My question was around diagnostics of the spillover effect, particularly because we lose power by doing that type of experimental design. So I wonder if you study any ways to diagnose the magnitude of the spillover effect and under which threshold we can go back to the completely randomization experimental design.
Yeah, so that's a very interesting question. So partly the way the motivation I see for doing these experiments in a more in a richer way than just the customer experiments or the product experiment is that it helps us actually learn about how we should do experimentation in the future. If in particular, kind of clustered experiments often involve a lot of loss of precision by limiting the randomization to between clusters rather than within clusters of similar products. And so if we do that all the time, and in fact these spillovers are very modest, then we're giving up a lot of precision every time. And so learning about that would be very important. So you may want to do one experiment to really focus on learning about these spillovers and just getting that knowledge so that you can do more cost-effective experimentations in the future. But to do that, it does mean you need to inject more randomness into some parts, and so you need to be willing to give up some power for the overall effects, at least in the short term. And exactly how to do that most efficiently, I don't quite know. But in some cases, you may be able to do this somewhat adaptively, where along the way, if you learn that these spillovers are not very substantial, you start switching to a more and more completely randomized experiment rather than a clustered experiment. And so, kind of getting this literature to connect more with the adaptive experimentation, kind of the bandit type ideas, I think would be very, very useful. So at the moment, we set it up kind of still in a completely static way. But of course, most of the experiments are done over time in a way that would actually allow for adaptation of some type.
Guido, thank you very much for answering our questions and starting the discussion. Seems like you've inspired a lot of people here to look at more complex randomization designs, and let's hope to see that effect in the future. Let's thank Guido one more time. Then we're going to move on to the next paper session. The first speaker is going to be Haruka Kiyohara. I hope I'm saying that right. Who came to us all the way from Tokyo, Japan, by the way. Right, the floor is yours.
Hi, I'm Haruka Kiyohara, an undergraduate student from Tokyo Institute of Technology. Today, I'm excited to share our work improving accuracy of a policy evaluation via policy adaptive estimator selection. So today, I'm going to talk about the emerging topic of policy variation, which is estimator selection for policy variation. But before that, let me just briefly introduce the policy variation formulation. And here, I put a typical recommended interaction where a user first comes to the system, and then we present some items to the user, such as books or magazines or fashion items. And then we observe a user feedback, such as click as reward. And now, in the daily operation, we are often collecting tons of valuable log-bounded feedback data collected by the behavior policy, which consists of variable information about how the user responds to the presented item. And today, we are interested in utilizing this variable informative log data to the policy evaluation task, which aims to evaluate the performance of a counterfactual policy using only offline log data. And thanks to the recent advances in policy evaluation research, we now have many candidate OP estimator used in practical situations. And to motivate us towards the emerging estimator selection problem, we're going to just briefly go over those existing estimators. So roughly speaking, OP estimators are categorized into three: model-based approach, importance sampling-based approach, and the combination of the both. And as we see in the morning tutorial session, model-based approach is known to suffer from a high bias due to model miscalculation, while the importance sampling-based approach, IPS, is known to suffer from a high variance when the importance weight is large. And the hybrid method, double robust, effectively combines both model-based and importance sampling-based approach and reduces the variance of IPS while remaining unbiased under the same condition as IPS. However, the remaining problem of DR is that it can still have a high variance when the importance weight is very large. And now, to further reduce the variance of IPS and DR, many OP estimator modifies the importance weight to more flexibly control the bias variance trade-off. And these are the example of such OP estimators. And in the presence of these very nice theoretically grounded advanced OP estimators, we now have an emerging question, which is which OP estimator we should use to enable an accurate policy variation, especially for the practical situation. And to answer this research question, we now conduct a synthetic experiment comparing mean scale error of various OP estimator using this behavior policy in the middle and a range of evaluation policy in the x-axis. And the result implies two important implications. So first, it shows that estimator selection is indeed a very important problem because the accuracy of policy evaluation results can change heavily depending on which OP estimator we use. Therefore, identifying an accurate or appropriate OP estimator is very important to enable an accurate policy evaluation. However, it also suggests that identifying such an accurate OP estimator is quite challenging in policy evaluation because the best estimator can change heavily depending on the configuration. For example, we observed that some suitable estimator in some configuration, such as yellow or green estimator in this configuration, can actually be one of the worst estimator on the other side of configuration, suggesting that estimator selection is very difficult because the best estimator can change heavily depending on the configurations, such as data size or evaluation policy. And today, we're going to make this seemingly difficult estimator selection for policy evaluation a bit more tractable by answering to the research question, how we can identify an accurate OP estimator or the most accurate OP estimator using only available log data. And this, adaptive data-driven offline estimator selection is very important to enable an accurate OPE, but has been underexplored in the existing literature. So we're gonna explore this emerging topic of estimator selection for forest evaluation. So let me now formally formulate the estimator selection problem for forest evaluation. And the goal of estimator selection is to identify the most accurate OP estimator, say in terms of mean scale error. However, identifying such an OP estimator is quite challenging because to calculate the mean scale error, we now have to know the true policy value, which is the estimate of policy variation. So therefore, instead of using the true mean scale error, we're gonna first somehow estimate the mean scale error using only available log data, and then we're gonna select the most accurate OP estimator based on the estimated MSE, and this can be one possible approach in estimator selection. And while there is no existing literature that formally formulates this estimator selection problem, we can now define a baseline approach, which we call non-adaptive heuristic, analogous to the real-world evaluation of OP estimator. And now, suppose we have log data from the previous A/B test. Therefore, the log data is collected by two different policies, A and B. And then, by regarding one of the behavior policy to be a pseudo-evaluation policy, we can now use its own policy value estimate as the estimate of a policy evaluation, and thereby calculate the mean scale error of given OP estimator. In this way, using this non-adaptive heuristic procedure, we can now derive this kind of result, which suggests that some advanced OP estimator works pretty well in a forest evaluation. However, unfortunately, this result only holds for the evaluation policy that is similar to the pseudo-evaluation policy or the behavior policy used in the previous A/B test, but does not hold for the evaluation policy that deviate from the behavior policy greatly. So this result suggests the need of an advanced estimator selection procedure that is adaptive to the given OP task or to the given evaluation policy. So being adaptive is the key in estimator selection, but how can we do that? And let me now introduce our proposed method, policy adaptive estimator selection via importance fitting. And the key idea of PASIF is that how about sampling the log data and constructing a pseudo-evaluation policy or pseudo-evaluation dataset that has a similar bias variance trade-off to the given OP task. So our idea is quite simple, and we are now subsampling the log data into the pseudo-evaluation and behavior dataset. And if we can successfully subsample the log data to simulate the similar distribution shift, and then we can now more accurately estimate the mean scale error adaptive to the given OP task, right? And based on this idea, what we're gonna do is to optimize the subsampling though to replicate the similar distribution shift. And now, defining the subsampling function as low theta and low theta XA to be the probability of the data point XA be assigned to the pseudo-evaluation dataset. And then we can now deem the pseudo-evaluation and behavior dataset to be collected by those pseudo policies. And using this notation, we can now optimize the subsampling function via importance fitting process or importance fitting objective that tries to imitate the original importance weight in the pseudo OP task. And giving a simple example of this importance fitting procedure, when we have this importance weight, 0.25 in the original log data, what we're gonna do here is that we are now trying to optimize the subsampling function to put the pseudo importance weight very close to the original importance weight. And thereby, we can now produce a similar distribution shift in the pseudo OP task, and thereby accurately estimate the mean scale error. So summarizing the key point of this PASIF procedure, PASIF is now producing the pseudo-OP dataset via adaptive subsampling or importance weighting process. And thereby, it enables an accurate estimator selection adaptive to the given OP task or to the given evaluation policy. So our idea is very simple and very intuitive, right? And now, let me finally compare the experimental result. And here, we compare PASIF with non-adaptive heuristic in 2 tasks. And the first is the estimator selection for policy evaluation. And the second task is the downstream policy selection task. In the first estimator selection task, we are first given log data, evaluation policy, and several candidate OP estimators. And we first apply hyperparameter tuning for each candidate OP estimator using slope procedure, which is a very nice hyperparameter tuning method in policy evaluation. And then we select the most accurate OP estimator using either PASIF or non-adaptive heuristic procedure. And we compare the estimator selection result for a range of evaluation policy. And here is the result. And we compare the regret matrix for estimator selection. Thus, we compare the mean scale error of the selected OP estimator and the true most accurate OP estimator. And seeing those results, it is very clear that our PASIF enables a very accurate estimator selection in a range of evaluation policy, while non-adaptive heuristic fails greatly when the evaluation policy deviates from the behavior policy greatly. So this result empirically verifies that it is very important to be adaptive to the given OP task to enable an accurate policy evaluation. And let me now also compare the downstream policy selection task, which aims to identify the most accurate OP estimate and the best performing policy from the given candidate policy. And in this case, we first apply estimator selection for each one of the candidate policy. And then using the selected OP estimator, we derive OP result, which is used to identify the best performing policy among the given candidate policy. And the key difference between PASIF and non-adaptive heuristic procedure here is that PASIF is now, can be adaptive to the given OP task and thereby can choose different OP estimators for different candidate policy. On the other hand, non-adaptive heuristic procedure can choose only one OP estimator for all the candidate policy. So this is the key difference between PASIF and non-adaptive heuristic procedure. And here is the result. And this time, we compare the regret matrix for policy selection. Thus, we compare the policy performance of the true best performing policy and the selected policy. And the result reveals that PASIF, improves the regret matrix of non-adaptive heuristic greatly, suggesting that it is enabling a very accurate policy selection by using different OP estimator for different candidate policy. So this result, again, empirically verifies that it is very important to be adaptive to the given OP task to enable an accurate estimator selection and also the downstream policy selection. All right, so let me now wrap up this presentation now. And today, I talked about estimator selection problem for policy variation, which is very important to enable an accurate OPE, but has been underexplored in the extant literature. And to enable an adaptive and accurate estimator selection, we propose PASIF procedure, which subsamples and optimizes the pseudo-OP dataset to accurately estimate the mean scale error. And the result comparing with non-adaptive heuristic procedure suggests that PASIF is not only beneficial for the estimator selection task, but also beneficial for downstream policy selection task, empirically verifying that it is very important to be adaptive to the given OP task in estimator selection. And we hope PASIF will help practitioners identify an accurate OP estimator for their own platform, for their own log dataset, for their own evaluation policy. Thank you for listening.
Thank you very much, Haruka. We have time for questions. I want to mention the QR code for the previous speaker still works for the entire session, so you can still ask your questions online. Do we have a question ready? Okay, then I have the privilege of asking the first question. You've looked at selecting different policies or making a selection from different policies. I do a lot of optimization. So my first question is, would this also make sense when we're doing optimization? So swapping between estimators while upgrading some policy.
I see. So you mean that you're gonna select the policy, best performing policy? Yeah. So yeah, in the policy selection task, we can also switch OP estimator for different candidate policy, and then we can enable more accurate OP estimation compared to applying a universal OP estimator for all the candidate policy.
Yes.
Yeah.
Now let's say that I have a policy and I want to have it with some parameters, a neural network or something, and I want to improve it. So, and I'm also using OPE to estimate my loss. Can it also tell me what the best OPE is for my model?
Yeah. That's
yes. Okay, and then this can change over time. Okay. So, what if we have a really large? What if I have a if I keep doing this optimization, isn't there some danger of overfitting? In the sense that if there's propensity overfitting or something similar, or is actually this OP selection going to mitigate it? It's going to make the risk less so.
Yeah, I'm
asking very open.
I don't have concrete answer for the question actually, but I think it is possible that our procedure can overfit to the data, but we are interested in the most accurate OP estimator for that data exactly, right? So yeah, I think even if we have some overfitting, maybe it is able to select an accurate OP estimator for that data, I think.
Okay.
Yeah.
Cool. Yeah, I would love to see future work.
Yes, thanks so much.
We have a question online, which is, if the behavior policy and the evaluation policy are very far away from each other, is the your method transferring the underlying hardness of the problem into an effective sample size?
Yeah, that's a great question. And actually, I was preparing for the appendix for that question.
Oh, okay.
That is true. And when the behavior policy and evaluation policy deviate so much, sometimes data size become very unstable. So we additionally regularize the constraint on the data size, and thereby we balance the importance fitting objective and the regularization of data size, and thereby estimate the mean scale error in a very stable manner.
Wonderful. Yes.
Hey, thanks. That was a great talk. Cool work. So what if what if somebody tells you, hey, this looks really great, but like I'm on a budget of time, or like this seems really expensive and I have so many policies I want to try out. I don't want to run your method like all the time for every policy. Could you use it just like a few times in the beginning to kind of map out the space of policies that you want to explore, and then just kind of generalize from that and like effectively amortize this computation?
Yeah, that's a great question. So thank you for asking. And I think one possible way is that classifying, several evaluation policy based on their, scale of the importance weight. And maybe we can, categorize the evaluation policy using the maximum importance weight, because it really affects the variance of OP estimator and also the, distribution shift. So I think categorizing evaluation policies that have similar distribution shift would work. And I think, thereby we can, reduce the computational cost. Thanks so much.
All right. Thank you very much for the presentation and starting the discussion. We have to move on to the next speaker. Let's thank Haruka one more time. Our next speaker is from the University of Washington, And it's I hope I'm saying it right. Lalit, John? Jane, sorry. Lalit, Jane. Let's welcome Lalit.
Great, it's great to be here, and thanks all for coming. It's been a great workshop so far, and I've enjoyed seeing all the talks. So today I just want to talk a little bit about some work I've been doing with colleagues at Amazon on running adaptive experiments and some of the pitfalls you can fall into, and some of the lessons that we've learned running adaptive experiments. So I'm going to kind of warn ahead of time that this is not as much a talk necessarily about solutions we've come up to, but lessons we've learned along the ways, and I'll put some solutions out there, but hope to raise some questions. Okay, so just to start off with kind of the setting that we're normally dealing with when we're at Prime, you can imagine that you have different contents that you're experimenting on. So these are all kind of messages to try to get people to sign up for Prime. And we have marketers who develop these messages, and at any given time, they may want to test 2 to 10 of these messages, right? So it's kind of a moderate number of these messages, and they're interested in figuring out what is the best possible one. Now, the time frame that they're running in is generally 2 to 3 weeks. It's kind of the standard ABN testing setting, and they want to understand what is the best performing message for driving various metrics, such as signups or conversions or clicks during that time period. Okay, so I'm going to just focus for a second on a real life example with just 2 messages, or something similar to a real life example with 2 messages that we encountered. And one of the ways that people often do this experimentation is, again, from a business perspective, right? You want to minimize your regret as much as possible or maximize your conversions. And so they may run an algorithm like Thompson sampling. And so this marketer basically ran an experiment, I think for 2 weeks with 2 messages. And this is the allocations that Thompson sampling chose to give to those 2 messages over a period of 14 days. Okay, so as you can probably see there, Thompson sampling is rather aggressive. It very quickly decides that it really likes one of the other messages. It changes its mind halfway through. And then at the end, it kind of fixates on message A. And so the marketer seeing this does something very natural, which we learned to do from A/B testing, which is they do a t-test at the end of this 14-day experiment. And that t-test leads to an insignificant result, as is bound to happen with t-tests. And the marketer stares at this and looks at the probabilities and says, well, the bandit was very convinced that message A was where to put all the traffic, so I'm going to choose message A. Okay, that's what happened. Okay, but this really bothered this marketer quite a bit. And so what they did was they then went and looked at a dashboard, and on that dashboard they saw what the daily message means was. And there I've plotted the means. So we kind of went back and redid this in simulation based off of getting results from A/B tests, et cetera, right? So for this example, we can pretend that I know the true mean. So I plotted the true means of the marketer in orange, of the 2 different messages in bold, and then kind of what the empirical estimates are as you run the algorithm along. And the marketer is very troubled because clearly orange is doing, message B is doing much better every single day, yet they've concluded the message A was the best. So intuitively, RMA does not seem correct. Okay, that's kind of the setup. So what happened here? And what happened here is probably a situation that many people in this room are familiar with if you've ran these kinds of adaptive experimentation procedures, which is, this is an example of what's known as Simpson's paradox, right? So in any given day, we're seeing the fact that one message beats the other. But if you plot the empirical means over time, which is this plot in the bottom left, you'll notice that in fact, message blue looks better than message A. And so the question you can ask is, so I bring this example up because I think it shows kind of the failings of Thompson sampling in settings where you have high amounts of non-stationarity. But I think one of the interesting things you can say here is, like, what is a metric that would have captured something more reasonable than the empirical mean, which we normally look at A/B testing. And so a natural metric of this is what I call the cumulative gain. And what the cumulative gain is if you just ask yourself the counterfactual question, if I had shown this message for all the traffic, which message would have been better? That is a very natural notion that's kind of invariant of the adaptive sampling procedure, right? So the empirical mean is this kind of weird quantity that's hard to understand, because when your means are moving around, the empirical mean is some weighted combination of the traffic you gave with what the true means were. So you could do this cumulative gain. So over the last few years, as we've kind of deployed these Thompson sampling experiments, we've often seen situations like this happen, where marketers are very unhappy with what our system's doing because we're trying to minimize regret, maximize for reward, and they're trying to get insights. And so in the process, we've learned a lot of lessons about what we'd want a system in an adaptive experimentation to do. And so I want to take a few seconds, and before kind of telling you our solution or our attempt at a solution, tell you a few of the lessons we've learned. So the first lesson that I think I want to emphasize, right, is that when you're doing experimentation, especially when you're in a world where you're like, hey, I have 5 to 10 treatments. Maybe for 2 treatments, it's not as interesting because A/B testing is as good as anything you could do. But regret minimization isn't always the be-all, end-all. In reality, in experimentation, you often want inference. And there's been a lot of great talks here on off-policy evaluation, and I think like that's definitely in that direction. But it's important to be able to provide inference to marketers who are not just producing content for, or not just trying to understand the results of today's experiment, but are trying to drive insights for what content to test on next. Traditional bandit algorithms for regret minimization oftentimes do not have enough power to drive this kind of inference. And as we've seen, they can introduce all kinds of biases. And especially in situations where you have system chocks, I think the kind of non-stationarity that we're seeing in Prime, where other marketing campaigns can affect our means, regret minimization can sometimes cause us issues. Secondly, oftentimes in these experimentation settings, and let me just check and see how much time I have. Okay. Secondly, oftentimes in these experimentation settings, what your goal is not just regret minimization, but to identify the best in hindsight. So as I said, the cumulative gain is a nice metric of what the best in hindsight is. And this is similar to kind of this idea of best arm identification, best arm identification literature, best policy identification literature. But it's a difficult thing when means are varying to know exactly what to define as the best in hindsight, right? Like, what does it mean to be the best arm when means are changing over time? And so we introduced this cumulative gain, and I'll say a few more words about that in a few minutes, but it's basically something you can estimate using IPS. Thirdly, we've really had a lot of impact that's kind of comes from having batch effects, right? And so part of what went wrong in this experiment is if you look at the very first few days of that experiment, arm A is better than arm B. And that kind of convinces the Thompson sampling, because we had a lot more traffic on those days than later days, and especially if you're kind of updating daily, that what it should do is put all its traffic on arm A, and then it takes a very long time between day 4 to 7 to try to correct that. So be extremely careful of these kinds of batch effects in adaptive experimentations. And then finally, one tool that we found extremely useful is to always provide always valid inference. So if you're not familiar with always valid inference, the idea is that these are confidence intervals that you can show on various statistics. For example, if you're looking at something like conversion rate or this cumulative gain metric that I'm talking about, that are kind of robust to sequential monitoring and do not suffer from some of the p hacking issues that you run into if you're kind of checking p values every single day. Okay, so providing these always valid confidence intervals has been something that really helps you check for, hey, am I having issues that come from non-stationarity? And I found it interesting that oftentimes people do not look at these plots of means every day. They just kind of look at what happens at the end of the experiment, which can be very dangerous in these adaptive situations. And so the question I'm kind of posing, and I'll say a few words about kind of what our solution to this is that our goal is to try to get to kind of a best of 3 worlds here. So you often hear people talk about best of 2 worlds algorithms, where they're best of both worlds algorithms, where you're trying to be robust to adversarial and stochastic data sources. But for me, I like to define this best of 3 worlds as algorithms that are mostly model agnostic. Oftentimes in settings like Prime, we maybe don't have a ton of contextual features or can't necessarily trust our contextual features. We want algorithms that identify the counterfactual best, because that's oftentimes the question that marketers will come to you with. They're like, what's the best message, right? And they want that with some statistical certainty. And finally, minimize the opportunity cost of actually running your experiment, which is what the business does. Now, it's not too difficult to kind of convince yourself in construct situations, and these situations have been constructed in the literature, that you really cannot have all 3 of these at the same time. It's easy to construct examples where it's like, hey, any algorithm is going to fail on these examples. But I think a question that's still rather open is, can you have algorithms that do a decent job on all 3 in reasonable settings? And our attempt to this was basically elimination. And now I'm going to ask just how much time do I have left? You guys are disagreeing. Can I take 5 because I started a minute late? Okay, great. So let me just kind of finish off by making some of these ideas more precise and telling you about our elimination-based method. So basically, this is a more concrete definition of what we define as this cumulative gain. Basically, under a model where we assume that the mean of an arm is constant at any given day, the cumulative gain is just how much reward that you would expect that arm to get in expectation. So here, mu s of I is the amount of traffic to arm I on day s, and ns is the amount of traffic you get on day s, right? So this is how much reward you'd expect. An easy estimator of this is just given by an IPS style estimator. So if Ri of s is the amount of traffic that you have on arm I on day s under some allocation for what traffic you put on each arm on a given day, then you can also define these all as valid confidence intervals. I'm not going to tell you the precise form of these. If you're interested, there's some issues that arise because we're using IPS style estimators that you have to be a little bit careful about when defining these all as valid confidence intervals, but I can talk about that a little bit later. And then finally, our method is kind of an elimination-based approach. And if you think of a situation in standard A/B testing, so here are my n arms, and here's some point in my experiment, and here's my confidence intervals kind of on these arms. What we do in standard A/B testing is we basically are taking enough samples on these arms, or hope we're taking enough samples on these arms so that these all get small enough so that one arm's lower confidence bound dominates all of the other arms' upper confidence bounds. Now, the problem with this approach is that it's extremely wasteful for some of the arms, right? We're splitting our traffic equally. So the question is, can you do something better? And that's what algorithms like Thompson sampling somewhat strive to do. But a very simple thing you can do once you have these all of its valid confidence intervals is just try to eliminate arms where the upper confidence bound, eliminate arms who at any point or on any day in this algorithm, you can deduce that you can eliminate because their upper confidence bound is less than some lower confidence bound. And so this is our elimination-based approach. It's fairly straightforward. You just run your algorithm, keep all of its valid confidence intervals on these cumulative gains, and then knock arms out when you think you can knock them out. I'll skip the precise algorithmic definition and just say a few words about what we can guarantee about this algorithm. And the answer is, in the stochastic setting, it's a pretty reasonable idea. It's not completely rate optimal. So people tend not to love successful elimination because if things are truly stochastic, it's a constant factor off of being rate optimal from both a regret perspective and a sample complexity perspective. But it is within a constant factor. So that's not too terrible. It does a good job on regret minimization, and it does a good job on finding the optimal arm. Our IPS version of this has an added benefit that in time varying settings, the one situation in which we can give a strong guarantee on this is if the gaps between arms are constant. So I know this was a setting that also came up in Lihong Lee's talk earlier. And this is, I think, a common setting that people see where you have some exogenous shifts that are coming each day. And in those settings, this algorithm will do a reasonable job identifying the counterfactual best. However, the problem with this, as you can imagine, is settings where you kind of have this crossover effect where one arm has a high cumulative gain than the other that knocks one arm out and you do a bad job. And so I'll skip this slide. We have some simulations where we basically show that successful elimination is pretty effective. And I'll just summarize by saying that, like, you know, adaptive experimentation in highly non-stationary settings, I think, is still a challenging thing. And the goal should be to try to get to these best of 3 worlds types algorithms. And I'm happy to talk more about this at our poster out there. Thanks.
Thank you very much. You've given us a lot to think about from the industry's perspective. Let's see, other questions from the room? Then I'll go straight to, we have an online question. You show that Thompson sampling is not great for the best arm identification in a non-stationary environment. Did you, between brackets, expect to experience the same with pure exploration bandits, e.g. track and stop?
That's a good question. So track and stop, we have not played a lot with, but I suspect it's something that we've discussed. Certainly the existing arguments out there would require some kind of stochastic assumption to be in place. But I think it's an interesting idea for, like, hey, if you always tried to track to the optimal distribution, given the set of means that you have up to a given point, would it do something reasonable? I think it's an interesting idea. It's something we've thought about, but haven't really played around with.
All right. I had a question myself. So I think at the latter part, you had to sort of skip through it, but I thought I saw, maybe I'm wrong, this is my question, that you were saying that in a non-stationary environment, you both want to you want to eliminate actions, but the non-stationarity makes it so that you kind of want to also add them back in sometime.
Yeah.
Yes. So is this the idea you make an assumption on like how quickly your confidence degrades or the situation changes?
Yeah. So the thing is that this is the failure point, I think, of these types of methods. And especially the danger in eliminating, which is like, what if something is really good on Tuesday, but really bad on Monday, and then you eliminate it by Sunday? My comment about this is that this is just something we tend to not see a lot in practice, which is why it hasn't been a big problem for us. But I think this is like where the interesting open question is, can you have algorithms that kind of do the right thing that are more robust?
I see. Very interesting. It reminds me, I don't know about you, but for me, if I would never be able to eliminate something, I think I would end up with 1 million options within a week. So it's kind of a very interesting direction.
Yeah.
We have time for a short question, if there is one.
Hello. Yeah. Thanks for the great presentation. So I have a question regarding your one of your 3 worlds. So you mentioned this. One of the words is minimizing the opportunity cost. So I wonder, what metrics do you use to measure the opportunity cost, and have you done any analysis or experiment to show how much opportunity cost saving that you can get from these different methods compared to the traditional A/B test?
Yeah, so sorry, I ran a little bit low on time, so I didn't have a chance to show it. But basically, the opportunity cost we're measuring, I just mean regret. So it's basically compared to playing the arm that kind of was the best every single day. How could you do, or rather I should say, compared to playing the arm that's the best in hindsight, how could you do? And these elimination-based methods are actually pretty competitive on that as well, because they very quickly knock out suboptimal arms. So I'm happy to say more offline.
Wonderful. Thank you very much for answering the questions. And sounds like you started an interesting discussion for afterwards. All right, let's thank Lalit once again. And our next speaker is from the University of Amsterdam. It's Philip K. Hager, I hope I'm pronouncing it correctly, who's going to talk about click models and IPS.
Wonderful. Thank you very much for the nice introduction, and good afternoon, everybody. I hope before the coffee break, you're sticking with me. My name is Philip Hager, and I'm presenting joint work with my supervisors, Martin de Rijke at the University of Amsterdam and Onno Zuter at Booking.com. And it's a work in which we compare 2 sort of families of approaches for unbiased learning to rank, so optimizing ranking models from position-biased click data, namely neural click models and inverse propensity scoring-based ranking models, and sort of to see how they stack up. So firstly, to catch everybody up, what is unbiased learning to rank? It's sort of the task and problem to optimize a ranking model, for example, for a set of documents that you might have for a query on a Google search. But instead of having supervised labels, how relevant each document in that search should be for that query, we try to infer this from clicks. However, as we've heard many times today, clicks are just a noisy and bias indicator of relevance. And for example, in this work, we specifically look at the well-studied position bias phenomenon, that items at higher positions just get more clicks than items at lower positions. So how do those 2 families of approaches deal with this? So the first one are click models, traditionally probabilistic click models, that try to create a model of generative models that predict actually the biased user behavior. So we're trying, like, given a set of documents, these methods try to actually predict where a user would click on. And on the right side, we've also heard this many times today, it's the position-based model that just assumes that each click happens on a document that is observed by the user here based on the parameter O for a rank K, and if the document was relevant here as Y. And so in this model, bias and relevance are latent parameters that we are jointly inferring by maximum likelihood estimations on like large click data sets. And if we would take this inferred document relevance Y here, we would have a point-wise ranker. So if we would sort by this sort of relevance. And it's a point-wise ranker because we infer this independently of all other documents and not in relationship. And so inverse propensity scoring is a different way to approach this problem. And in this case, we are reweighting clicks by the likelihood of a user observing that clicked item. And these IPS-based methods were explicitly introduced to sort of improve over IPS-based approaches in I would say 3 ways. So the first one is they decouple the bias estimation part and the relevance estimation part in 2 separate steps. So the bias can be, for example, then just estimated in online randomization experiments, and the training then only takes care of the relevance estimation part. Secondly, click models typically inferred a single parameter for each query document combination, and you need a lot of observations of the same query document pair. And these IPS approaches usually use document features to represent these pairs, and so you generalize over multiple observations by using feature vectors. And lastly, the first IPS approaches introduced were pairwise and listwise rankers, which are usually to be assumed to be stronger ranking methods than pointwise. And so this is why I would state IPS approaches at the beginning were not really directly compared on the same data sets with click model approaches. So why look at this now? So first of all, both approaches are still intimately linked. So they are both using the same assumptions of user behavior, like the PBM user model or the cascade user model. Secondly, we've seen the introduction of neural successors to those traditional click models. For example, we've seen 2 tower models recently that also use features to predict document relevance or the bias part of a click model. And so lastly, we've also seen the introduction of pointwise IPS methods. So we asked ourselves the question, is there sort of a link between those 2 families of approaches? And we want to look at this link maybe theoretically and compare their ability for unbiased relevance estimation, as well as compare those 2 approaches empirically in the same synthetic click simulation. So let's look closer at both methods. So in this work, we use a neural implementation of a position-based model in which we use a neural network to predict document relevance from document features. So here we have a simple 3-layer feed-forward network with a sigmoid activation from document features X to predict our document relevance Y. And we represent position bias just by a single parameter that we have for each rank K. And we predict clicks just as the joint probability of examining a rank and a document being relevant. We can fit this model just by minimizing binary cross entropy between the click predictions that we have and our actual observed clicks in our data set. And so, as mentioned before, the IPS approach directly tries to predict document relevance. So in this setting, the model is only the relevance network part of our click model, but it's otherwise the exact same architecture. The debiasing here happens in the loss function, and we actually adopt binary cross entropy extension from Saito et al., which weights clicks inversely to the position bias. As you can see here, we are directly predicting relevance Y hat, but our observed clicks in the data set, which are CDK, are actually sort of scaled by the estimated position bias. So how do those 2 approaches compare when it comes to inferring unbiased document relevance? The IPS method I just showed you is provenly unbiased when, first of all, the click behavior of a user actually follows the PBM user model. And secondly, when our estimated position bias matches actually the true occurring position bias. the concept of unbiasedness is a little bit tougher to quantify for a click model, because here document relevance is a parameter of the model to be inferred. And recently, Harrie Oosterhuis has shown that click models that jointly infer both bias and relevance at the same time are not always consistent estimators of document relevance, because we can have rankings in which even an infinite amount of clicks would not really help us differentiate if this is right now a position effect or an item effect. So jointly inferring both parameters is dependent on the data for the consistency. However, in this work, we asked a different question. So in the IPS approaches, we assume we know the true position bias for unbiasedness. So we asked the question, what if the click model would also have access to that true position bias? Would the click model then actually also be unbiased in this case? And so for the full math, I refer you to the paper. However, we can find that indeed, if we would initialize the click model with the true position bias and then only learn the relevance part, we can also see that we are optimizing actually the loss for unbiased document relevance. So in theory, both approaches should be somehow working the same. We can also visualize both loss function here for a single document of relevance of 0.5. And one interesting observation might be that when you have an infinite amount of clicks, you can see that on the right side, the IPS loss actually always converges to the same loss function. However, the click model's loss is actually getting lower in magnitude with an increase in position bias. So here we simulate different levels of position bias on the same item, and the magnitude of the loss, while the minimum is still at the right place, at the click model gets lower for items placed at lower positions. Intuitively, you can think about an item at a lower position, since we are predicting CTR rate, will have a very low CTR rate. So we are in general in a very small loss. And that's an intuition that's important for later. However, let's first look at some synthetic experiments that we ran to compare both approaches. We use a very common click simulation setup in unbiased learning to rank. We use 3 large learning to rank data sets, MSLR, Yahoo, and Istella. We generate clicks by sampling a query and the related documents. We pre-rank those documents with a basic production ranker, which is just a lambda mart trained on 20 queries. So we get something that is, well, better than just shuffling at random, but it's definitely not a great ranking. And then we sample clicks according to our user model. So we have no user model misfit in this setting. And actually, here are the results on, and the x-axis is log scale. So we simulate up until 100 million queries actually on all 3 data sets, and those are experimental results over 10 independent simulation runs. So I'll hopefully guide you through this. At the bottom, the green line is actually this production lambda ranker that we are using to pre-rank our documents. Above that, in light blue, we have a click model and an IPS approach that does not correct for position bias at all, actually a naive approach. And you can see even with 100 million sort of sessions, this is still not at an optimal performance because it's a biased approach. Above that, in dark blue, we have a click model that jointly estimates position and relevance effect. And this is on some data sets a bit more unstable and definitely has the highest variance of the approaches. And most importantly, in this chart are the top 2 lines where we see that on Istella and Yahoo, the click model and the pointwise IPS approach in red here have a small but significant difference, even after 100 million sort of sessions, even if both approaches have access to the true position bias. So why is that? First hypothesis could be we have seen like differences in the loss function. Might there be an issue with the tuning? Do we need like a higher learning rate for the click model? We detail this extensively in our paper, but we are quite confident that hyperparameter tuning is not the issue. We consistently saw this difference. Secondly, we hypothesize that this difference, that items at lower positions in the click model contribute less to the overall loss, might become an issue when we start generalizing over shared document features. So this is actually a thing we can observe in this 2-item sort of toy setup. We have here in orange an item that is not very relevant, but always observed, and in red, an item that is very relevant, but only observed in 10% of the cases. Both approaches correctly infer the correct document relevance when we calculate the loss independently, but once we compute their combined loss, so average, for example, over both documents because they share all their features, the IPS approach actually optimizes for an average of both documents, while the click model is much more biased towards the item that got a higher exposure, just because it has more impact on the loss. We verify this hypothesis with 3 more experiments. The first one is if sharing sort of features might be an issue, we should not see this issue when documents share absolutely no features. So we generate 10,000 one-hot encoded document vectors with like a randomly assigned relevance. And in fact, in this setting, both approaches converge to the same sort of perfect relevance inference that is possible in the setup, and they perform equivalently. Second of all, when we start in the synthetic data set to randomly introducing collisions basically between documents, where we basically project one document onto another and to force them to share the same features, we should see the click model deteriorate quicker than the IPS approach. And this is again also what we are seeing. And lastly, what might be a bit counterintuitive is that this effect gets just stronger or worse with a presence of a stronger position bias, even if it's known to both approaches. So here we are simulating from the left side no position bias, to the right side a very strong position bias, and you can see that the IPS approach almost consistently recovers the full performance under no position bias, while the click model deteriorates with an increase in known position bias. So let me wrap up this work. So we compared both a neural click model implementation and a pointwise IPS approach on equal footing, and we saw that both approaches optimize for unbiased document relevance under this strong and sort of very artificial condition that the true position bias is known, and relevance is estimated separately for each query document pair. However, we also make this observation that the neural click model seems to be affected by position bias when we start generalizing over shared and sometimes conflicting document features. I want to stress this is obviously only for the setup we've used in this paper. The QR code is a link to a paper and a link to the code. And thank you very much for your attention, and I'm happy to take your questions. Thanks.
Thank you for the fascinating talk. Do we have questions from the audience? Great. Oh, no. Okay. You get to go first.
Hey, thanks for the talk. I was wondering, so you currently fixed the propensities to be exact. Do you know what happens if you slightly misestimate the propensities? How are both methods affected? Are they affected differently if you slightly misestimate the propensities?
I haven't tried out extensive, like I have a broad intuition, but I'm hesitant to share. So I'm like, the experiments aren't done yet in the position bias mismatch sort of setting, which you start to have a mismatch. No, I don't have a good answer for that yet.
All right, I wanted to ask a question myself. So on, can we go to slide 12?
Sure.
So for both of these methods, the bias is known, right? So there's
yes.
this is so do you think that this is happening due to the log that's being used in the loss? That seems to be the main difference, right? So the IPS just upweights the click rate, the other one multiplies it with the log of the relevance.
Yeah, I mean, I think in general it seems to be an issue. I might go back to this slide that that the target of our prediction just get smaller and smaller. So even if you have a very relevant document, if it's in 10th position, the CTR rate you're predicting over time will be very, very small. So we are operating in very small scales. And here I show like the loss is smaller, but actually you can verify also that the gradient updates will be much smaller. So if we then start a document that has sort of this kind of magnitude and like this kind of magnitude together, right? We have much more sort of chance to minimize the loss with the higher exposed item here. And yeah, so I think since this is mitigated exactly by dividing sort of after the log, and then so your target is scaled, we don't have this issue here.
Right. Yeah. Right, because it's not just the scale; it's a different shape. All right, where maybe it's scaled in the horizontal axis.
Exactly. This is then the log doing this.
Yeah. So my follow-up question would then be: would this also apply to something like a regression loss, like a mean squared error? I know you didn't look at this, but would you think?
It should, in some ways, yes.
Okay.
Yeah.
Out of time. Let's thank Philips once more for his presentation.
Hello. In this talk, I'll present our work on CLEAR, causal explanations from attention in neural recommenders. In recent years, recommenders based on deep neural networks have demonstrated state-of-the-art accuracy. Notable among these are attention-based recommenders, which leverage the transformer architecture to scale well with model and data size. However, these models are not transparent, and it is not clear how to interpret their recommendations in a meaningful way for humans. This may hinder their adoption, as explainable recommendations can lead to greater trust and increased human engagement with the automated system. In this work, we present a method for learning session-specific causal graphs that enables extraction of meaningful explanations for recommendations given by transformer-based recommenders. During a session, a user sequentially selects items to interact with from lists of items presented by the system. We assume that the human decision process for selecting which items to interact with is complex and consists of multiple decision pathways that may diverge and merge over time. These pathways may be influenced by variables unobserved by the system along this process. For example, a user may watch a movie either because she favors a certain genre or because she likes a certain actor. Since each session is independent of other sessions in terms of the decision process that stands behind it, we would like to model that process as a unique structure per session. During training, a recommender system captures knowledge about the human decision process from the training data. This captured knowledge later enables it to provide recommendations for each session. In order to provide explanations for these recommendations, we are asking a trained system the following questions. What knowledge about the human decision process is captured by the recommender? Can we learn a causal graph that encodes this information? How can we use such a causal graph to explain the recommendations? Given a session I, we are interested in asking a recommender two types of questions that will shed light on the logic behind recommending item A to a user. What previous interactions in the session led you to recommend item A? What would you have recommended had the user performed a different type of interaction during the session? Our approach is to model the decision process as a causal DAG, which consists of observed and latent variables. We examine attention-based recommenders pre-trained on large data sets, learn a causal graph for each session, and suggest it as a means for human understanding of the model. Note that we do not claim that attention-based recommenders learn causal graphs for sessions. Instead, we consider the learned causal graph as a projection of the model. Next, by considering the recommendation as part of an imaginary session, we extract an explanation set from the causal graph. At a high level, our method consists of three stages. 1. Abductive inference. 2. Causal discovery. And 3. Explanation. We'll go over them at a high level in the next few slides. The goal in the following slides is to explain the logic behind recommending an item in a given session. For this purpose, as an example, we will look at the movie viewing history of a user, where our task is to explain the logic behind the next recommended movie for this user. In our approach, we use a pre-trained attention-based neural recommender, which generates a self-attention matrix between all items in session I and predicts the next item. In this example, for session I with items I1, I2, I3, I4, the model predicts item I5 as the best candidate for recommendation. In the next stage, abduction, the goal is to learn the decision process that led the recommender to recommend I5. For this purpose, we define an imaginary session consisting of items that the user interacted with in session I and the recommended item from the previous stage, item I5. We pass the imaginary session through the recommender model and extract the attention matrix of the last self-attention layer in the model. Once we have extracted the attention matrix for our imaginary session, we evaluate the correlation matrix from the attention matrix and use partial correlation conditional independence testing to extract a causal graph. This graph models the human decision process as captured by the recommender model. In our paper, we use the iterative causal discovery algorithm to extract the graph, but note that any constraint-based causal discovery algorithm can be used for this purpose. The extracted causal graph enables answering two types of questions about the logic behind the recommendation. One, why have you recommended item I5? And two, what would you have recommended if a change was made to the session? We do this by constructing what we call a potential influence tree that reflects the influence of each set of items, a potential influence set, on the recommended item. Although a potential influence set identify nodes that are conditionally dependent on the recommendation, it may not be a minimal explanation for the specific recommendation. That is, omitting certain items from the session alters the graph and may render other items independent of the recommendation. Hence, we provide an iterative procedure to create multiple candidate explanations by gradually increasing the value of the search radius. The explanation is derived from the smallest potential influence set. For empirical evaluation, we use the BERT for Rec recommender model, pre-trained on the MovieLens 1 million ratings dataset, widely used in education, research, and industry. We compare CLEAR to a baseline attention-based algorithm that uses the attention weights directly in a hill-climbing search to suggest an explaining set. We use several measures to evaluate the quality of the explanations. The explanation set contains the items that are responsible for recommending the top one item only, amongst the other top items in the recommendation list. It needs to focus on the reasons that distinguish the first item from all the rest of the items. Such a set should be minimal, since a smaller set is less likely to influence other items, and it is more interpretable to humans. The explanation set should be specific for the original top one recommendation, and the replacement recommendation should be one of the other original highest ranking recommendations. We quantify the quality of the replacement recommendation by measuring its position in the original list of recommendations. These are the results of the experiments that we executed. The left figure shows the distribution of the explanation set size for the various sessions. Most of CLEAR's explanation set sizes are 1, which is very interpretable, and the largest set size is 3. This is much lower than the explanation set size of the baseline method, which goes as high as 25, not interpretable. In addition, we compare the explanation set sizes of the two methods for each individual session. From the right figure, it is evident that approximately 50% of the sessions are of smaller set sizes for clear, and only 8% of the sessions are of smaller set sizes for the baseline method. Another set of experiments examined the second quality metric of the position of the replacement recommendation. For a new recommended item, we look at its former position, meaning its previous position within the top 5 list. The left figure shows how the former positions of the new recommended items are distributed. Lower is better, as the replacement recommendation was highly ranked in the original recommendation. We can clearly see that clear's new recommendations are of lower former positions compared to the baseline method. Similarly, the right figure shows the relative gain of clear compared to the baseline method. To conclude, we presented causal discovery from attention-based neural recommenders. The constructed causal graph is a projection of the user's decision process as perceived by the neural recommender. Various insights can be extracted from this causal model. Here, our method demonstrates generating a causal explanation to why a specific recommendation was given in a specific session, and in addition, it provides a counterfactual reasoning of what would have been recommended if the user had made different decisions. Thanks for listening. For any questions, please feel free to contact us at this email address.